And Bismillahirrahmanirrahim. Assalamualaikum and good morning to all the participants and viewers. Let's begin our event today with a multi-talk Fatihah to get more blessing, inshallah. So my name is Hassan. I'm the chairman for the morning session. On behalf of the iNuSTEC committee members, I want to welcome you. And so to thank you for all the contribution and support that you've given despite of the COVID-19 pandemic. We are very happy and excited and truly humbled for all the posters that we have received, which are more than 60 of them, which will be presented during the event. So in conjunction with the iNuSTEC 2020 Nuclear Science, Technology and Engineering Conference, we are also organizing RPO refresher course on the second day and third day of the event, and also the first ever online nuclear debate, which features local universities such as UIKM, UKM, as well as UNITEM. So this event is organized by Malaysian Nuclear Society, together with University Tenaga Nasional, and also supported by all the other industrial partners such as RS Solutions Network, and also local government agencies, national nuclear agencies, as well as local universities such as UKM, UIKM, and all of them. We are very thankful for all the support to the event. And also, we do hope that you guys stay throughout the sessions, because in the afternoon, just before the lunch break, we will be having Kahoot challenges, which will give you a lot of exciting prizes. And today, to start the event for the morning session, we are happy and excited to have one of the famous and well-known figures in the Malaysian nuclear community, which is no other than Professor Sung Min Choi. He is the head of Department of Nuclear and Quantum Engineering at KAIST, which stands for Korea Advanced Institute of Science and Technology, Republic of Korea. And he's also the Vice President of Korean Nuclear Society. We are very happy and excited to have Professor Sung Min Choi. And today, he will be delivering a talk with the title of Nuclear Energy to Combat Climate Change. So without further ado, I'll invite Professor Sung Min Choi to deliver his keynote speech. Thank you.
Good morning. First of all, I'd like to thank the organizer, especially Professor Aziz, for inviting me to this wonderful venues. Actually, this is a new experience for all of us, talking to over internet and then do the conference like this. And then this new experience, whether we like it or not, most likely change our lifestyle. Well, I'd like to talk about this nuclear energy for combating climate changes. Maybe since I was asked to talk about neutron scattering, I'll also briefly mention it as well. And next slide, please. So many of you, actually, I have many good friends who visited KAIST, but just in case, those of you who haven't visited KAIST yet, this is the view of the KAIST. And KAIST has about 600 faculty members and then 1,000 10,000 students, including masters, including undergraduate and graduate. And next slide, please. So our department, Nuclear and Quantum Engineering, was established in 1980. It was the time that very early days of Korean nuclear program. In fact, just 2 years after Korea Unit 1 started, which was built based on turnkey. And then 1980s Korean nuclear program tried to do localized nuclear technology, and then to build our own technology by 2000 or so. And by 2010, our department tried to do leading role in the Korean nuclear program, and then do more in the global arena of the nuclear R&D. Next slide, please. Our department consists of 4 different areas: nuclear fission energy and nuclear fusion, and then medical and radiation science and technology. We have 16 faculty members and then 260 students. About 15% of students are from foreign countries, and then we have I think we had many students from Malaysia as well. We are very pleased to have them. So let me briefly talk about our what we are doing in our department, and then move on to the original topic. Next slide, please. Korea, and including our department, has focused on the large power reactor. So most recent one Korea developed and built is APR 1400 on the left, which is a 1.4 gigawatt power nuclear reactor. Now, these days, our department is focusing on the small modular reactor or micro modular reactor. This is very compact, and the power is of course small, and then it can be even built in factory and transported to the site it is needed. And another thing we are emphasizing is that autonomous operation to minimize the work of operators, so that we can increase the possibly safe. There are many hurdles to overcome, but we are trying to do as much as we can. And the next slide, please. Actually, this one's supposed to be the movie, which is the power plant, the small micro modular reactor, 12 megawatt, transported to some area, but due to this PDF transferring PDF form, it is just a photo. Sorry about that. So anyway, this will eventually, I think, by having a small or micro modular reactor, not only we can transport it, we can expand the role of nuclear power, not only just electricity generation, but for other purposes like hydrogen production, and also for transportation, like a large vessel, a ship, a submarine, and so on. Next slide, please. I'd like to share this one with you. Many of you have known, maybe already know. This is NASA's Perseverance to Mars, which has a nuclear battery. It is on the way. I noticed that it is about halfway to the Mars, and then it is planned to arrive February sometime. So this is the only way, nuclear energy is the only way to do this kind of let us large rover do the work in the very harsh conditions. So this one, you can tell that the future of the nuclear energy is for mankind. And next slide, please. One of our faculty member has a dreaming something very drastic one. So previous nuclear battery is not rechargeable, it just decay and then recharge. Of course, it takes you can use very long time, like 10, 20 years, 30 years. But one of our faculty members is dreaming it. Can we have a rechargeable nuclear battery? It's just dream for the moment. But if it happens, it changes everything. It changes this battery business, and also it will change this nuclear waste issues. Hopefully, sometime we can have a power to control nuclear state more precisely, so that we can use it for battery, and we can use it for we can get rid of the problem of nuclear waste. Next slide, please. So our department also do nuclear fusion research. Recently, we strengthened our program. Couple of years ago, we had only 1 faculty members. Now we have 3 faculty members in the nuclear fusion and plasma. So since Korea is involved in the ITER program, so it is also very important for us. So, and also very near KAIST, there is a fusion reactor called K-Star. So we are closely working with them. And then also our faculty members do various application of a plasma. One example is the plasma propulsion using Hall effect thrust to handle things in our satellite. Actually, this whole thruster is being used for our Korean satellite in the space. Next slide, please. Next, okay. So we also do radiation application for medical and industrial purposes. So we develop a diagnostic system and also detectors and the imaging algorithm system, and then also industrial application as shown here. Next slide, please. Another thing very important for us is the radiation for new materials, like neutron produced in research reactor, and then X-ray produced by synchrotron accelerate radiation sources, and so on. We utilize to study materials, high entropy alloys, and then nanoparticles, and flexible ceramics, and so on. Also, one of our faculty members is working very hard to understand radiation effect on materials using modern technique called nanomechanics, which can understand the radiation effect in a very, very small scale. Next slide, please. So this is the Hanaru Research Reactor. Some of you may have visited there. It has been very unfortunate that this reactor was down almost 5 years. Now it has a permission to operate. It is starting up. Hopefully it comes back fully for our research for materials and so on. Next slide, please. So since I'm working on these nanoscale materials, let me very briefly talk about what our group is doing very recently before I go to the nuclear energy issues. So these are the building blocks, like nanoparticles our group made. And then, in fact, not only this shape, we can control the size and shape and very precisely. Then we can have a very broad spectrum of monodisperse building blocks. Next slide, please. So, in another word, we can have a sort of a periodic table of nanoparticle. As we all know, all the materials we are using is some combination of element in the periodic table. Likewise, this nanoparticle can be, you can imagine this kind of periodic table. Since nanoparticle can change, you can control the shape, but also you can control the size. In principle, we have a three-dimensional periodic table. So next slide, please. Having this, we can make many different combination of particles put into different symmetry. If we can, then we can have new properties, so-called emergent properties, which can produce new functionality and for new application. Next slide, please. Next slide, please. So one example is that this is the micelle assistant formation of gold nanoparticles paratis. So if we use this combination, not only we can make a new some symmetries, we can have a sort of a stimulus responsive spiralis, like atomic crystal change do their phase transition. We can do phase transition behavior in nano particles palettes as well. And in these cases, this one is the nano rod on substrate, which can be precisely and then individually embedded in the silica matrix, which can be very stable, wide in a wide range of temperature range. Then it can be used for molecular detection and so on. Next slide, please. So this is a larger view of so-called this gold nanoparticle superlattice of different particle shape. So this is early days, but as you can see, it's like these nanoparticles are used like as an atom, a super atom, and then you can make a different kind of crystals. So in the long run, we should be able to make a bigger and also more controlled way, and not only single type but also binary or ternary is a mixture of nanoparticle forming a different kind of symmetry, and hopefully it can be used for new purposes. Okay, next slide, please. Well, now let me briefly talk about nuclear power in Korea. Next slide, please. And currently, we have 24 units operating and 4 units under construction, and then 2 units actually in a strange status, so-called construction stop. It is not cancelled, but construction, it is very early stage, but it is stopped for the moment. And then 2 units are shut down. Gori Unit 1 and Walsung Unit 1 has been shut down. So this is the planned nuclear power plant was actually cancelled. This is a rather strange recent energy policy of the current government. Well, so somewhat our Korean nuclear community is somewhat struggling. And next slide, please. But at the same time, there was also good news, is that last year, Korean nuclear power plant, so-called APR 1400, received a design certificate from US NRC. In another word, APR 1400 can be built in US. And this design was also certified EU as well. So it can be built in the European country as well from a safety point of view. And next slide, please. As we may know, so Korea exported 4 nuclear power plants to UAE. And then this year, first unit number 1 in UAE, built in UAE, has been connected to the grid. So meaning that now it is supplying supplying electricity to the UAE. So we are very pleased, and also UAE is very pleased to have a first power plant, nuclear power plant operating in the region. Next slide, please. Well, so that's a background. So sort of a short update for Korean nuclear status. Well, so actually, when I was asked to give a presentation, I was thinking about what should I talk. Well, there is technical issues, but what is more important, maybe a more general issue can be useful to share. And even though all of you know about this, recent experience in Korea from a public acceptance point of view, I think I'd like to share some of the things with you. So as you know, climate change, well, it is more appropriate to say climate crisis. Well, next slide, please. Well, we are experiencing COVID-19. It changed a lot our daily life. So we are doing this conference over internet, and actually all the lectures over internet online. And our faculty meeting is over online, and then so it changed a lot. So we wear mask all the time except you are alone. So that changed a lot. So it makes things very difficult. But climate change could be much worse than what COVID-19 is doing to us. So, well, next slide, please. If you look at what our energy sources humankind used so far over the years, so this is in terms of fraction. All the days we used wood and coal came in, and oil and natural gas, and the nuclear came in most recently. All the energy, there is a time that it peaks and goes down. It's not because everything is depleted, because new source of energy coming in. But here, except nuclear, everything is fossil fuel. That's what we have used, humankind have used. And that's what caused the problems, as you know. Next slide, please. So as you know, this CO2 emission is rocketing over the years, especially over the last 50 or 60 years or so. That's the problem that humankind never experienced over the years. Next slide, please. Well, this, as you know, so the global energy, temperature, increased about 1 degree compared to pre-industrial era. And next slide, please. This will cause a serious problem everywhere. We are already experiencing. Actually, Korean temperature, Korean weather has been changed quite a lot. It's getting close to tropical weathers. Right? There is some good aspect of being a tropical weathers, but it changes the many things. We used to have a four clear season, but the boundary seems to be a little bit changing. And then a couple of years ago, we experienced 41 Celsius. That's the highest temperature I ever experienced in Korea. So things are changing. We are experiencing it very closely. So as you know, IPCC agreed to try to declare that we should go for 1.5 degree below before we have too much trouble. But it is very challenging, and then it is not too far from reaching 1.5 if we do as usual, we do now. So if we continue to that, it will continue to go up very easily. So we need to plan it out. But how do you plan it out? It is very, very difficult issues. Next slide, please. So by 2050 or around that, so to meet these 1.5 degree issues, we need to make this CO2 emission net zero by 2050, which is not too far, only 30 years away. And then, as you can see here, we have to just rapidly drop these emissions. Of course, it doesn't necessarily mean that we are reducing CO2 in the air. It will just flatten out. So to flatten out, we need drastic changes. Next slide, please. Well, if we look at this one, it is clear what we should do. So fossil fuel, whichever it is, coal, oil, gas does matters. So, but even gas, it is direct emission is much less, about less half of the emission from the coal. But if we consider the indirect emission effect, is essentially comparable. So Korea, not only Korea, all the world use a lot of coal, a lot of gases. I'm sure, I think Malaysia also use a lot of gases as well. So we need to getting rid of this fossil fuel is very, very challenging. But we need to go to biomass, nuclear, hydro, wind, solar, and so on. So among these, nuclear is the produce the most smallest amount of the CO2. Essentially, practically emission-free energy is the nuclear. So these days, wind and solar receive a lot of attention and then investment from all many countries. But it has a serious problem of intermittence. So it cannot produce energy during the night when it is raining or snowing. Wind is a similar situation as well. So it has a nice advantage, but it has a very serious problem. And also it needs a lot of area because energy density is fairly low. But on the other hand, nuclear, as we all know, energy density is much higher. Typically, it requires only 1% of land compared to 100 times less land than the wind or solar, typically. So in terms of resource usage, nuclear is much better. So we should go for nuclear. That's inevitable. Hydro is also very good choices, but it depends on these places. Korea is hopeless for hydro because geology doesn't allow it. And the next slide, please. So there are recent report from IEA that about nuclear power. Usually IEA doesn't produce a report about nuclear, but this is very special cases, International Energy Agencies. So it talk about its role for the climate changes. So simply, nuclear power is a clean energy, and nuclear power and hydro form the backbone of low carbon electricity generations together. So it made a recommendation, a few recommendations for the government. So first, ensure existing power plant can operate as long as they are safe. Actually, that's the most economic way of producing nuclear energy for the moment. So, for example, in the case of United States, most of the nuclear power plant received life extension of 20 years, additional 20 years. So most of them received 60 years of operation, and some of them recently received the 80 years of operations. And also they suggested supporting new nuclear constructions and then new nuclear technology development and so on. So that's what we should try to do. And then that's what many countries need to do. But next slide, please. This Fukushima accident, 2011, and then this made a big changes nuclear sectors all over the world, especially Korea. And also there is a lot of public fears induced by this kind of movies and then something like this. Next slide, please. So this is a nuclear accident movies in Korea a few years ago. It was a very bad movie for us. A lot of people watched it. There is a public fear also generated by this kind of movies. Next slide, please. Well, I'd like to say this one. This is the truth lies in the data. So this is by Professor Steven Pinker, who is the psychologist at Harvard University. Next slide, please. So let me briefly look at what he said. So people are terrified of nuclear power, the most scalable form of carbon-free energy, because of images of 3 Mile Land, which killed no one, Fukushima accident, which killed no one, and Chernobyl accident, which killed fewer people than are killed by coal every day. So if we look at the real data, actually nuclear is very, very safe compared to others. And just next slide, please. Deciding just this public or just things without looking at the data, as he says that it's like deciding something based on omens or on dreams and then and so on. So we need to look at the data very clearly. Next slide, please. So if you look at the data, this is the death rate from energy production per terawatt hours. As you can see here, nuclear energy is the safest in energy compared to all others. In fact, nuclear, the next slide, please. If there was no nuclear, in fact, many people could have died of the air pollution and so on. So recent the paper in 2013, they estimated what if there was no nuclear, and then if we look at that one, essentially nuclear saved 184 million people, which people doesn't actually recognize. People always talk about this, how many people died of Chernobyl and how many people died of Fukushima. In fact, Fukushima, there is no one died of radiation exposure. There are people who died during refugee period, but it is, if they didn't go for refusing, they could have survived. So that tells us radiation, fear of radiation is more dangerous than radiation itself. So next slide, please. So how to overcome this radiation fear? Actually, fear of nuclear, which is the fear of radiation. Next slide, please. Well, we try to talk about what is the radiation and what is the natural radiation background. We experts all know about this. Many people know about this, but most of people doesn't know about this. Well, next slide, please. In fact, all the universe, space is full of radiation, and then Earth can be also, fortunately, of course, Earth is protected by Earth's magnetic field from solar or solar wind and space radiation mostly. Next slide, please. So yeah, next slide, please. Space radiation comes in all the time. Next slide, please. Another thing is that Earth is actually a lot of nuclear radioactive materials in it. In fact, if you look at the core, there is uranium-238, thorium-232, and gallium-40. It has a lot of them, and then actually radioactive decay of this element produce about 20 terawatt. which correspond to about 20,000 nuclear power plant of 1 gigawatt summer. So in fact, this is the energy that keep this Earth's core cooling, preventing cooling of the Earth's core. And in fact, this is very important to keep the Earth's magnetic field available. Next slide, please. So all the elements, things grown on Earth has radioactivities, natural radioactivities. Next slide, please. And then our human body also contains small but appreciable amount of radioactivities because we eat something from Earth. So I'm about 70 kilograms. So in my body, I have a 7,000 becquerel of radioactivity in it. So it means about 7,000 radiations comes out from my body. If I say this one to general public, they are very, very surprised. But that's what it is. And next slide, please. And also, we are experiencing many different radiations from X-ray, CTs, and then air travel, and so on. But in fact, all these kind of the radiation I'm talking about here is larger than radiation exposure from a nuclear power plant, which is much less than 0.1 millisievert per year, even though they live around there. And then, but people are still worried to live around the nuclear power plant. Next slide, please. So these days, we are doing a lot of activities to talk to or to interact with the general public in Korea. So our faculty members go online and go on TV and participate in the various public debate and writing in the newspapers. And also students, our department, make an event for public communication, and they make an event to meet the general public here and there. And we also often go to a high school as well. And the next slide, please. So this is the program I'm learning these days. I didn't expect I was doing this similar thing a few years ago. So together with the faculty members of our department, Seoul National University, actually all the faculty, many faculty members in Korea, we make YouTube. So and then lectures and then and so on. So it is on YouTube. If you are interested, you may check it out. Next slide, please. Well, this is the current general public opinion on nuclear energy in Korea. In fact, it is not bad at all. It's about 30% of people who support nuclear power. 70% of Korean people support nuclear power. About 30% are against nuclear power, which is not bad. But this one was the other way around some years ago when there was some movies, and also there was an earthquake in Gyeongju area, which is about 5.6, which is not huge, but it influenced the public opinion very much. But right now, we have a 7-to-3 ratio of public opinion. So even though current energy policy is rather strange, but considering this public support and considering the necessity of the nuclear energy to combat the climate change, I think eventually at some point our energy policy will be changed, and then globally more nuclear energy use is increasing, and then I expect it will be increase faster in coming years. Next slide, please. Once again, nuclear is the most scalable form of carbon-free energy, and I would say most environmentally friendly energy. So to overcome that, we need to develop new technology again for more safer nuclear power plant. But at the same time, we should work very hard to communicate the general public to get rid of unnecessary or overdue fear of nuclear and radiations. Next slide, please. Thank you very much for your attention.
Thank you so much, Professor Sumit Choi, for the great sharing and also the great presentation that has been given. We really appreciate it. Professor Sumit Choi has shown us the advanced technologies that are currently being developed in KAIST, and also has reminded us how important it is to have nuclear energy to actually address the climate change issues. We really appreciate your effort and time, and also your commitment to iNuSTEC every single year. Thank you so much. So we have come to the main session of the event, which is the opening ceremony of iNuSTEC 2020. I would like to invite our beloved Professor Madya, Dr. Abdulaziz Muhammad, the President of National Nuclear Society, to deliver his welcoming remark.
Assalamualaikum. And I'll do back telecast through YouTube. So the world can listen and watch this step 2020. So first of all, I'd like to express sincere eminence gratitude to Deputy Vice Chancellor in Institute of International, Professor Dr. Muhammad Jambi bin Yusuf, for officiating the iNuSTEC 2020. There's a quotation officer with special cost and initial debate in the history 2020. And also, this also allowed the intense lecturers from the students from the third media to be in the main committee member and as secretariat to make the teleconference successful. And I also would like to congratulate Dr. Siti Aisyah bin Hussein for her promotion of the Director General of the Media recently. And I also like to extend big thanks to the Minister for the years of supporting member among his activity. Honorable guests, leaders, speakers, and viewers and students. On behalf of NS and others who are contributing to the message, I would like to welcome all the meeting guests, keynote speakers, and participants for the 3 days teleconference of the International Nuclear Science, Technology, and Engineering Conference 2020. I'd like to share with you what we listening to society. So actually, NS only existed nearly 32 years. So, and so far we have a membership about 20,000 of them. And then it's about 60%. The member is the age between 30 to 50 years old. So this is very important because at this range of age, there are a lot of energy, a lot of capability, and then a lot of risk-taking. So I hope, as the president of MNS, the young members should continue to participate and to engage with our. Also, MNS very much lucky because we have a lot of memorandum understanding with other World Nuclear Society, like American Nuclear Society, Canadian Nuclear Society, European Nuclear Society, Korean Nuclear Society, Japan Atomic Energy Society, China Nuclear Society. So this is a chance for the member to use this networking to either to get more knowledge from this community or to make a lot of friendship to this community. Okay, then we back to the nuclear education. I think all of us know nuclear has been a lot of contribution to humankind activity. Nearly everything. Okay? You can see this application that can be used from sea to steel, from agriculture, industry, medical, and but also for the destructive use of what for it. And recently, the pandemic COVID-19 have seen another application of nuclear. Okay? So under the IEP guide and IEP sponsorship, so people from nuclear community have come up with this test kit for the reverse transcription polymerase chain reaction, or known as RT-PCR. It is a nuclear DNA technique and very quick to detect the virus causing COVID-19. And we are very honored because Malaysia is one of the countries as a familiar to you. And about this conference, okay? So the theme of this conference is the sustainable nuclear science and technology for well-being of mankind. Okay? So as I got told the schedule, there are about 70 papers and posters presented by the speakers and what is speakers at this Then for keynote speakers, we have three keynote speakers from overseas. One from South Korea, another one from Berlin, Germany, and the last one is from USA. So the first keynote speaker already delivered his presentation. Professor some and Choi, old friends. And for the keynote two, we have Professor Nicole Kajang from from Berlin, Germany, on the title of electron energy. That's another exciting area to be explored by young scientists in Asia. And the third keynote is from United States, Texas and University, Professor Greg and Reiner. And he'll be talking about the role of nuclear science professional in security and emergency response. So this is another topic. It's very, very relevant to the nuclear community to convey the public how we manage and how we look at the safety and security issues. It's a prime to make the useful of nuclear methods. Okay? One more thing. Okay? In this nuclear conference, we are proud to host the Radiation Safety Leadership Course for Radiation Profession Officers in collaboration with the RA Solution Team Member Hub. And also we have the nuclear debate that will be online. So usually we have this clinical debate. Okay? So for this debate, the participants come from the three universities, four universities, right? University of International, University of Bahasa Indonesia, University of Technology Mara, and University of Technology Malaysia. So all these students are undergraduate students. And the Nuclear Science Conference has come along since 2010. So this conference is an ideal platform for scientists, researchers, and stakeholders in nuclear science and energy engineering to share experience and exchange knowledge in the related area. And the iNuSTEC has surpassed the various challenges that the nuclear science technology has faced over the years and has adapted to the changing public perception. From having the conference with a small participant in 2010, we start to slowly have the participants now with 100 participants. And for this conference, we have about 80 participants registered to the iNuSTEC. Okay, finally, I'd like to thank to supporting organization like National American Joining Society, American Society of Relations Section, RO Solution, University of Bahasa Indonesia, University of Technology Malaysia, University of Technology Malaysia, University of Malaysia, University of Maya, and others, Student Nuclear Club and Association. And also, I'd like to thank to Scientific Council to support this conference. Also, I'd like to thank to Dr. Nasri, Dr. Shukri, Dr. Hassan, Rogema Madeha from United Nuclear Energy and Engineering Group, or known as GREEN, for their tireless effort to make this iNuSTEC conference successful one. And also, I'd like to thank the moderators and judges for the debate, RA and RedTech for RPO discussion course, and my most thank to Dr. Farida, Honorary Secretary Emeritus, Dr. Judy, Honorary Pleasure. Without them, this teleconference may not become a reality. So my wish is all these participants and you have a nice teleconference and have a fruitful knowledge in this virtual conference. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Dr. Aziz, for the remark. We really appreciate and truly appreciate your commitment in making sure that iNuSTEC happens every single year. Next, I would like to invite our honorable guest, which is the Deputy Vice Chancellor of University Tenaga Nasional, Professor Dato T.S. Dr. Muhammad Zamri bin Yusuf, to deliver his welcoming remark and to officiate our event today. Please welcome Professor Dato Dr. Muhammad Zamri bin Yusuf.
Rasulillah wa ala
Tidak dengar.
honorable guests, conference presenters, and participants, ladies and gentlemen. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good morning. It is my great pleasure to welcome all the distinguished guests, keynote speakers, and participants to the 3-day virtual conference of the International Nuclear Science, Technology and Engineering Conference 2020, iNuSTEC 2020. I wish a special welcome to all the eminent speakers from Malaysia and nuclear experts from overseas, such as from the Republic of Korea, the United States of America, and Germany to iNuSTEC 2020, and thus making this conference a truly international conference in spirit. I'm very glad and thankful that you are willing to spend your precious time and sharing your knowledge and vast experiences with us, especially for the young budding nuclear scientists and engineers in Malaysia. I would like to also express my sincere thanks to the organizing committee for inviting me to say a few words, and I'm humbled and deeply honored to be invited to officiate this conference. I was informed that this is the third time that University Tenaga Nasional, UNITEN, is organizing iNuSTEC with MNS. The first was in year 2010 and the second was in year 2017. iNuSTEC 2020 is especially more significant and challenging as the conference has to be held online for the first time in history in line with the Conditional Movement Control Order CMCO SOPs due to COVID-19 pandemics which are currently raging the world. I was also informed that UNITEN students from the Squad Media UNITEN played a big role in bringing this conference online to all of us. Congratulations to our talented students from Squad Media UNITEN. Indeed, nuclear science and technology development is closely intertwined with the World Wide Web, networking and computing development. The demand from the former drive the latter to the forefront. And it was actually the scientists who worked at CERN, Geneva, who first invented the World Wide Web to share the vast nuclear data across the world. And high-performance computers are used extensively on the grid to run complex nuclear simulations. Ladies and gentlemen, this conference is jointly organized by the Malaysian Nuclear Society and Malaysian Nuclear Agency in collaboration with several local universities and vendors. I wish to thank all the committee members for their tireless efforts in ensuring the success of this virtual online conference. I was informed that in this iNuSTEC 2020 conference, there will be more than 70 papers to be presented by the keynote speakers, invited speakers, and participants. Parallel to the presentations, like what we always have every year, the conference will also host 2 other events, which are radiation safety refresher course for radiation protection officer in collaborations with Aerial Solutions Sendirian Berhad, and also the Nuclear Debate 2020. Both of these events are also held online, virtually. And the Nuclear Debate 2020 involves students from Malaysia's local universities. The theme for this year's conference is Sustainable Nuclear Science and Technology for Well-being of Mankind. Indeed, I'm very convinced that this conference is an ideal platform for scientists, researchers, and stakeholders in nuclear science, technology, and engineering to share experiences and exchange knowledge in related areas. iNuSTEC has indeed come a long way since its inception in 2010, and it has surpassed various challenges that the nuclear science and technology has faced over the years and has adapted to the changing public perceptions towards nuclear. Back in 2010, the conference only has just 20 to 30 participants annually, compared to almost 100 participants and exhibitors that we have now. Indeed, we have come a long way in making the conference a huge success. So congratulations to all those involved. Ladies and gentlemen, allow me to share a little bit on the University Tenaga Nasional involvement in nuclear education. In providing students with sound knowledge in nuclear, the College of Engineering, University Tenaga Nasional, UNITEN, where I was dean before, initiated the introduction of several technical elective courses in nuclear engineering and nuclear technology within the mechanical engineering department. To ensure the effective implementations of the nuclear technical elective courses, cooperations and collaborations with several other institutions such as the Malaysia Nuclear Agency and University Kebangsaan Malaysia UKM were established. We also established cooperations with foreign universities, agencies, and companies such as Chulalongkorn University in Thailand, Tokyo Tech in Japan, King's and SNU in Korea, the IAEA, Rosatom in Russia, TEPCO in Korea, and Hitachi GE Nuclear Energy in Japan. Since there is limited nuclear facilities in UNITEN, cooperation with the Malaysian Nuclear Agency is vital to ensure that our students have the opportunity to use M&A nuclear facility. Exposing our students to the Triga Mark II research reactor and NDT laboratories at M&A helps our students to understand the physics and applications of nuclear technologies better. Besides, research activities are also conducted at M&A facilities. In strengthening the cooperations, a memorandum of understanding between UNITEN and M&A was formalized back in December 2010. Alhamdulillah, currently the College of Engineering is still offering 2 nuclear courses, which are Introductions of Nuclear Engineering and Nuclear Policy, Security and Safeguards as technical elective for all engineering students in UNITEN. These elective courses are very popular among UNITEN students. Every semester, we have about 50 to 80 students enroll to take these courses. In addition to that, in every academic year, there are always UNITEN students who undergo industrial training and conduct final year projects in nuclear-related fields. Furthermore, at postgraduate, master's and PhD levels, there are also students who specialize in nuclear science and technology. It is hopeful that these students will be the ambassadors in supporting the establishments of nuclear power in Malaysia in future, should Malaysia decide to go nuclear. Distinguished guests, ladies and gentlemen, I would like to conclude my speech by encouraging all the participants to participate in all the presentations and discussions through the digital platforms for the next 3 days. On this note, and with lafaz Bismillahirrahmanirrahim, it gave me a great pleasure to declare the International Nuclear Science, Technology and Engineering Conference 2020, iNuSTEC 2020, officially open. I wish everyone a successful, safe and fruitful conference. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi ta'ala wabarakatuh. Thank you very much.
Thank you so much. Thank you so much, Professor Dr. Muhammad Zamri bin Yusuf, for his welcoming remark and also for officiating our event today. We truly appreciate the commitment given by you and also UNITEN in supporting all the events conducted by the Malaysian Nuclear Society. All right. So, for all participants and viewers, please make sure you enjoy the rest of the day with the presentations that will be given by all the participants. And don't forget, before the lunch hour, before the lunch break, we will have the Kahoot challenges with the rewarding prizes. Hope you guys will stay till the end and till the end of the conference, which is on Thursday. So now I'm going to pass this session to my next colleague, the Honorable Dr. Muhammad Shukri bin Yahya. Thank you.
Hello, Assalamualaikum and good morning. Welcome to iNuSTEC 2020. My name is Muhammad Shukri bin Yahya. I'm a lecturer with UNIPEN, and today I'm giving the honor to moderate session 2A of iNuSTEC 2020. Session 2A is about energy and infrastructure. So basically, things that are not on the other groups. Okay. So we have now about 7 presenters in this session, and each presenter is given 20 minutes. So you have about 20 minutes, including presentation plus question and answer. Okay, so you can ask question via comments on the YouTube link, or for the presenters who join the meeting via WebEx, you can also talk to us via WhatsApp. So we have 2 ways of communication. Okay, before we start, a little bit of housekeeping notes. For the presenters, please kindly scan the QR code on the YouTube link so we can register your names. And then I think that's all. Okay, so let me start with my presentation. Okay, Bismillahirrahmanirrahim. So this is my presentation. The title is a preliminary quantitative study on the economic impacts of deploying a nuclear power plant in Malaysia using Empower. So this work is actually completed by my final year project student, Sharvesh. However, he could not attend the meeting today, so I'm going to present on his behalf. And the project also is co-funded by Dr. Nasri using his grant. Next, please. So here are the outlines of my presentation. So for today, we are going to talk about the impact of deploying nuclear power in Malaysia, and we are going to use the Empower software developed by IEA in order to assess the economic impact of building and operating nuclear power in Malaysia. So for the outline, first I would like to talk about the statement, why we want to do this topic. Then we also want to talk about the objective. And later I will give you a brief introduction to Empower, then a little bit of result and conclusion. Okay, so next please. Okay, so I think most of us knows that back in September 2019, about 13 months ago, Malaysia Nuclear Power Corporation, MNPC, was officially disbanded by the iNuSTEC. Okay, that marks the end of our latest attempt at embracing nuclear power. It is sad. Okay, why it is sad? Because to me personally, I know that MNPC has been doing very good job. It was formed in 2011, January 2011, by Prime Minister Najib. And for the past 8 years, it survived Fukushima nuclear accident. It survived the first election won by Dr. Sri Najib. And then it has been recognized by IEA and other international organizations to be one of the best nuclear organizations in the world. However, when there was a political shift from Barisan Nasional to Pakatan Harapan back in 2018, this marks the shift of our stand on nuclear. Before this, we were planning to put nuclear power as one of the options for our fuel policy. But when the shift happened, Pakatan Harapan, as we know, they put in their manifesto that they would like to end all the efforts by Barisan Nasional to embrace nuclear power. And because of that, they did that a few months after that. So why it is sad? Because to me, they do not even allow MNPC to disclose or do a presentation on what we have done. I mean, we have given MMPC about 80 million of ringgit of funding to do some studies. So they have done 3 big studies on the nuclear power infrastructure, but we were not even given any page of the report. So the report, the 8-year study was shelved together with the disbandment of the MMPC. So to me, the reason why MMPC was disbanded seems political. So it's not based on technical justification or economic studies. So it's just political. It seems a populist decision. So because nuclear power is not popular, so when they shove MNPC, they are putting a stop to nuclear power. So if it is a shame, it is sad to me as a nuclear power supporter, but it is what it is. Okay, I cannot do that. We cannot do much. Nevertheless, we know that nuclear power is green, and nuclear power is also the only proven baseload technology to help combat the worst consequences of climate change. So therefore, I personally believe, and I strongly believe that it should remain an option for Malaysia. Unfortunately, there was a change in political landscape in Malaysia again back in February 2020, early this year, where Pakatan Harapan was lost power, and then Perikatan Nasional took power, and we have a new minister for science and technology, YBKJ. From my understanding of what he presented on his Twitter and his social platform, he seemed very supportive to all innovation and science and technology, including nuclear technology. So I have been told that the new Act, the PLB Act 1984, is now undergoing through discussion for enactment. So we hope that after the parliament sitting on the budget is done, and after a few of government issue is solved, we can open up the issue on the sitting for nuclear, the new act for nuclear Atomic Energy Act 1984. So because of that, I think there could be there is still a future for nuclear. So because it's green and it's a proven technology, and we cannot run away from nuclear power. So because of that, I took up the challenge. Okay, should we build a nuclear power plant, NPP is nuclear power plant? What will be its economic impact on our nation? I'm interested in economic impact because, first of all, we know a lot about technological advantages of nuclear power, and we know a lot about technological disadvantages of nuclear power. So we've been talking about that, but we never really go and study if we build a nuclear power, what will be the impact on our nation? Okay, what will be the impact on our economy? So that is why I assigned this topic to one of my students, and we come up with this research. Next, please. Okay, so the main objective of the research is to estimate the economic impact of deploying an NPP in Malaysia. And specifically, we are going to use IA developed tool called Empower. So a disclaimer, like we should tell that we do not pretend to be economists. So because we are not, we are just engineers. So what we present is the numbers from the Empower calculated spreadsheet. So, and this is just an academic exercise using Empower. So we want just to yield the ballpark values of the NPP economic impact on Malaysia. So our numbers are very, very dependent on our assumption, and our results are limited by the modeling constraint of the Empower itself. So please don't quote us for any economic studies. Just an exercise we hope to expand that you expand the topic, and we hope to enhance the accuracy of our result. Okay, next, please. So before I really start on the subject, I would like to talk about Empower. What is Empower? Empower is a short for Extended Input-Output Model for Nuclear Power Plant Impact Assessment. Okay, it is developed by IEA through what we call a Coordinated Research Project, CRP. It started in 2014 and the CRP project was ended in 2018. So what it is actually is a compilation of mathematical equations using from economic sector to help evaluate the impact of nuclear energy on the macroeconomics indicators. So when we say macroeconomics is the whole total economic, which include employment, export levels, and GDP. So the good thing about Empower is not only limited to nuclear power, nuclear energy. So you can use the same spreadsheet to analyze impact of other form of energy on the key macroeconomics indicators as well. So if you're interested in oil and gas, so you can just replace the data from nuclear energy with the oil and gas data. So what I show at the bottom of the page is a screenshot of the Excel spreadsheet itself. So if we open the spreadsheet, there are actually many tabs, and there are tabs for input output, there are tabs for result, there are tabs for parameters and other things. So it is not really friendly to use. It is also not really easy to decipher the result. But the good thing about this tool is Excel. So it's quite flexible for you to change it. Okay, if you want to program it with C++ or Fortran or any other fancy language, you can do it. So because this is just a basic framework for the calculation. Next, please. So this is the mathematical model. So I'm not going to go into details because these are mathematical equation for the parameters that we are going to estimate. So if you need further details, I will be happy to share with you my source. Okay, but basically, these are typical equations used by economists in order to determine or to calculate the macroeconomic indicators that we are interested in. So next, please. Here are the nomenclature of the equation that we just presented before. Next, please. Here are the block diagrams of the spreadsheet. So you can see that the block diagram looks a little bit cluttered because the formulas are dependent on each other. That's why the arrows are a little bit, this is not quite straight arrows, okay? So you need to start from one, which are the input data, input output data, and then goes to 2 and goes to 3. So the good thing about Empower is you don't have to understand this diagram, okay, the block diagram. So you can just put in the values of the input that you require, and then it will calculate for you. So if you need to change some of the parameters of the equation, so you can refer within this block diagram and go to the right tab on the Excel spreadsheet. Next, please. And then Empower enable 4 scenarios if you are interested to calculate. So you can see that this is like a subset. So scenario A is subset of scenario B, which is a subset of C, and which is D. A is the direct indirect effect of the nuclear power. Then B is the induced effect of the nuclear power, and C is the labor market response of the activity, and D is the feedback on financing instruments. So if you like to see the impact of nuclear power deployment based on the direct indirect effect only, so you just turn on model A. If you're interested in labor market response without the feedback from fancy infrastructure, so you turn on C. If you like to see the total scenario, just click on D. So D encompasses A, B, C. Okay. So next, please. So for the input data, Sharpesh actually get the data from first Department of Statistics, and then Asia Data Library, then we from ILGA, from National Energy Handbook, and also from MNPC. We have source from MNPC as well for many of the technical data. So we assume that the construction of the reactor will be 12 years, and then we distribute the construction cost evenly throughout the 12 years. And then we also use this same data to extrapolate to fit for the entire construction and operation periods. This actually not the right way to do it, if you ask me, because first, the data that we have is publicly sourced data. So what we have will not be the data from the latest reactor on the market. So the data that we have is actually from the Gen 2 PWR. So when we do this, that's all that we have. We don't have access to data from EPWR or AP1000 because those are confidential. So it is what it is. So we have to make do what we have. Because of that, there will be some limitation on the accuracy and some limitation on the reliability of the analysis. And furthermore, when the research was performed, COVID-19 wasn't around yet. So we did not anticipate a pandemic to happen. So in our result analysis, we assume it is as usual. So what we presented will not be accurate because the world is changing due to COVID-19 pandemic. So we are still trying to get familiar with the new norms of the pandemic. So because of that, the result of this study needs to be revised and to be updated with the new change in the world. Okay, next, please. Okay, so this is the importance. So I'm short of time, but I will go very fast. So you'll see that 2020 is we assume that the construction start in 2020, which is very optimistic. Okay, but this is just a scenario. We want to say that, okay, we start constructing the reactor today. So this is what will happen to the GDP of the nation. So you can see that we are about 15,000, and then in 10 years we almost double the GDP if we start to build nuclear reactor today, assuming that all the financing and all the funding has been secured. Okay, if we do that, so in 10 years our GDP can easily be double based on the Empower calculation. Next. Then the output also changed. This is output from nuclear power plant. So it also goes up very fast. So it goes from 3,000 to about 6,000. Okay. So we know that having nuclear power will help to energize the economy, and based on the calculation by Empower, it is shown like this. Okay, it improved our hypothesis. Next. This is on this disposable income from nuclear power plant. We assume we have about 31 billion at the beginning, so the income is distributed and dispersed as we construct and operate the reactor. Next. Next slide, please. And then the employment, demand of skilled labor actually increases as we construct and operate the reactor. So you can see that for model C and D, we have positive employment, net employment throughout the period of construction and operation. So which is a positive impact on the economy. So next. So I have 1 more minute, so let me finish. So as a conclusion, so what we saw for Empower data is what we expected. We confirm what we predict. A nuclear power plant be can only be positive on the economy. It can help to be our catalyst because it twofold the increment of our GDP, and we have about 25% to 100% increase in output and disposable income, and it significantly reduce our employment rate. However, please note that when we do the calculation, we put up a budget of 31 billion, but for the revision, we know that a budget exceeding 51 billion easily has to be required for the construction operation of the utility. So next, my parting remark is actually NPP has impacts on Malaysia beyond economy. So we know that it has a positive impact on the economy based on the study from the Empower software. But it also, if we have NPP in Malaysia, we have to enhance the appreciation of the scientific knowledge because now we we have to embrace nuclear power. So we have to embrace quantum physics. We have to start teaching the modern physics to our students. And also having a nuclear power, we also have cultivate self-awareness in our safety culture. So we will uh, we will easily have to develop better safety in our working culture, and also having nuclear power will open more doors for more doors for spin-off like radiation, energy, and innovation business. And nuclear power can also be a pride of our nation, like like Petronas. And also, the most important thing is nuclear power is a proven green solution for the climate change mitigation. And that's all from me. Okay. So thank you. And if you have any question, you can send an email to me. Okay, let's move on to the next presenter, I think. Okay, Assalamualaikum warahmatullahi and good morning. So welcome back to iNuSTEC. So we are still in session 2A and we apologize for the delay in the arrangement of the session. This is the first time we are doing the online conference. So hopefully after this we will have a smooth operation. But right now we have the honor of having Mr. Dr. Mark Dennis Musa, a dear friend of mine from Malaysian Nuclear Agency. He has a PhD in Tokyo Tech technology. His expertise in basically modeling of the quantum physics. So he will present a paper on rate of energy dissipation in Benjamin equation calculation of fission. So without further ado, I will give the floor to Dr. Mark Dennis Musa. All the best, Doc.
Hello. Hello. Good morning, everyone. So I'll be presenting on Legend equation, but this time with regard to rate of energy dissipation. So next. So the content is roughly on a little bit on introduction, and then I'll be showing you what the methodology, results, and after the conclusion. Next. Next. So basically, nuclear fission is just the splitting of a nucleon into two or more fragments, typically two fragments. Usually there's three types of nuclear reaction, which leads to fission. These are particle-induced fission. Particle-induced fission can be neutron-induced fission, it can be proton-induced fission, or even electron-induced fission. Fission can also be induced via fusion reaction. We have, for example, two very large nuclei. For example, you can have a mercury mercury collision against another mercury nucleon, for example, and then afterwards it will produce a compound nucleus and then split up. Or it can be spontaneous fission, which is fissions by decay. When this fission occurs, we will usually start with a compound nucleus, and this compound nucleus will deform, and after it will separate. And after it separates, usually it will immediately release or emit additional particles, usually neutrons and gamma rays. Next slide. So when this occurs, we will have fission of observables. So usually the main fission observables are total kinetic energy of the split fragment, or it can be the yield, or we can also measure the yield. Basically, we are counting what fragments are produced. And other fission observables include from neutron emission and also from gamma emission. Using Langevin equation, the total kinetic energy and the fission yield can be directly calculated. And if we include an additional step, for example, with Hausser-Fudge-Barsch, we can also calculate from gamma and from neutron emission. Next slide. So far, there are three types of Langevin equations, the code I mean. We have three-dimensional Langevin equation with macroscopic transport coefficient. We also have three-dimensional Langevin with microscopic transport coefficient. And we also have recently four-dimensional Langevin equation with macroscopic transport coefficient. This could contribute significantly towards the in recent years towards successful characterization of fission yield and total kinetic energy for fission of common actinides such as uranium 236 and plutonium 240. When in here I mean the in terms of the compound nucleus. For example, if you have uranium-235 and then it was induced by neutrons, you will form this uranium-236. And the same calculation also proceeds when we have uranium-236 decaying via spontaneous fission. Okay. We also managed to reproduce the experimental systematics for fission fragments, total kinetic energy yield. And we have also been successful in explaining the anomalous transition in total kinetic energy and yield for fermium-256 to fermium-258. What actually happens here is that in fermium-256, we have double peak fission yield, and in fermium-258, we have a single peak fission yield. So this transition has always been mysterious to a lot of theoreticians, and a consistent explanation has been successful previously, and we have been able to explain it with Langevin equation. With Langevin equation, we can also identify the standard, the super short and super long fission mode. This is basically the length of the nucleus when it becomes it fission. And we have recently examined the role of lead-208 in super heavy fission, which we believe is the reason why we have a three-peak fission yield in super heavy fission, especially at very low energy. Next. So here is our objectives. In the far future, in the long term, we hope to develop four-dimensional Langevin equation with microscopic transport equations. But for the moment, we only hope to bridge the gap between macroscopic and microscopic transport coefficients. So what we, at the moment, our problem is we have macroscopic friction that are too large, simply. If you look at the figure below, the black line is the macroscopic friction, and the other lines, the red, the green, the colored lines, they are all microscopic friction at different temperatures. And so, in most literature, in our own calculations, we reduce this friction by multiplying it with a factor of 0.27. However, as you can see, this can barely match fission process at somewhat high temperature, nuclear temperature. So if we wish, for example, to simulate the behavior of fission at very low temperature, for example, which is common in thermal process, for example, thermal neutron fission, and also spontaneous fission, we need to be able to use this macroscopic friction at low temperature as well. So the reduction factor has to be fine-tuned. To do this, we need to study the rate of energy dissipation, or at least for now, uranium-236, to derive a better estimate of the reduction factor. Next. Next. So, to be able, so in Langevin equation, the first thing we need to do is to describe the shape. So, to describe the shape, we use two-center shell model of marine Griner with next parameter of 0.35. So on the right, you have two figures on top, and then bottom, the top figure is on the potential energy for the nucleus, and on the bottom, the shape of the nucleus. So in this model, we simply fit a harmonic oscillator for each of the fragments on the left and on the right. And in order to obtain and in the middle, we fit it with a quadratic equation. Yes. This is in order to be able to obtain the potential for the nucleus when it was undergoing splitting. So in four-dimensional Langevin, we have four parameters, which is the shape is described by U mu, and we have four parameters, which is Z0 over R0, delta 1, delta 2, and alpha. Z0 over R0 is basically the separation between two fragments. Delta 1 is the deformation shape on the right, and delta 2 is the deformation on the left. And alpha is just the mass asymmetry. And so with this, we will be able to describe the shape of the nucleus. Next. Next, please. Hello. And once we are able to describe the shape, we can calculate the liquid drop deformation energy by subtracting the energy deformation when for the given shape and from its spherical shape, and that will give us the liquid drop energy. As for the shell correction energy, we have to calculate the single particle energy, and then we sum it, and then you subtract from it the average energy of a normal distributed energy. And the same is also done for the pairing energy, but it's slightly more complicated. And then we correct this the correction energy with either full shell or electric formula. And in this work, most of it is done using current work we are simulating thermo-induced neutron, so we use full shell correction energy. Next. So if we plot all of the potential again for each shape, this is what we will get on the figure on the left, on the right. Sorry, on the left is if we just use liquid drop deformation energy, but if we add the shell contribution, we will get the figure on the right, the potential energy. Next. As for the transport coefficient, we have two transport coefficients, the macroscopic and the microscopic transport coefficient. The mass in macroscopic evaluation, the mass tensor is inspired by Werner-Wheeler equation, and by solving this equation, we will obtain the mass tensor. the friction tensor is obtained by Rayleigh dissipation function. So I need to emphasize that at the moment when we calculate the rate of dissipation energy, this is the equation that we will use. And for the microscopic transport coefficients, the mass and friction tensor are obtained using linear response theory. So from the response at, if you look at the figure QM, we derive the equation of motion for the oscillator and then extract the corresponding mass and friction tensor. Next, please. And once we have all these ingredients, we can put it into the Langevin equation. So basically, as you can see, Langevin equation is just two equations describing the change of shape and the change of momentum. And we have other parameters, for example, the noise. So in the first equation of the Langevin equation, it's just the momentum divided by the mass. But on the second equation, we have contribution from the first term is the conservative energy, and then the second term is kinetic energy. Third term is the friction, and the last term is from the random random force. So RV here is white noise, and it's modified by Einstein. We obtain it from the modified Einstein relation. And this equation has to conserve energy. So from there we can obtain the intrinsic energy, and this intrinsic energy is equal to AT squared. Next. So when we apply the changes in shape on the potential energy surface, we will get these lines, and this line shows at the end where is our final configuration. So this is the trajectory, and this trajectory depend on both, mostly on the potential energy surface and partly on the transport coefficient. Next, please. Next, please. Hello. If we look at the result, if we look at the friction tensor, macroscopic friction in 4-dimensional and macroscopic friction in 3-dimensional are literally the same, with minor differences, mostly because of the differences in bit size. This is for friction corresponding to Z0, and if we next, please. Next, please. And if we look at friction tensor with regard to alpha, it is also very similar. However, when we look at the dissipation energy, here is the rate of dissipation energy. Next, please, sorry. So we look at the rate of dissipation energy. The average dissipation energy is 10.6, and we basically start very stable in the beginning, but it will drop rapidly just before fission and drop, and then it will increase slightly, few moments before fission. But if you look at three-dimensional longevity, in the next slide, please, next slide. You can see that the average dissipation energy is very different. Previously, we can see that the rate of dissipation energy on average is around 10, and now it's less than 1 MeV per second. And we do not see the stable region previously, and we only see the rapid eventual decline in dissipation energy. So now let's look at next on the friction tensor of microscopic friction. So if you notice, although the figure looks essentially the same, we can see that the scale is not. So the change in the scale of friction changes from 0 to 100. And if you look at 0.1 MeV, there's all blue. And when we look at temperature of 4 MeV, we begin to see a large, it becomes slightly greener. And if you look at the scale, I'm not sure if you can see it or not, but the friction increase for 0.1 MeV all the way up to from 0 to 25, around 25 MeV, which is very small compared to friction for 1 MeV, which is all the way up to 70, and 2 MeV all the way up to 140, and for 4 MeV all the way up to 250 MeV. So although they look the same, the amount of friction steadily increased with higher temperature. Next, please. And the same is also can be seen with regards to friction for alpha, where we see that the friction for 0.1 MeV temperature is only up to 120, and then this increased to 154 at 1 MeV. And 2 MeV is around 800, and for 4 MeV it is around 1,200. But as if you remember, this friction is still smaller than compared to macroscopic transport coefficient. So let us look next, please. At the rate of dissipation energy in 3D Langevin with microscopic friction, we can see that a slight increase in dissipation energy from 0.1 MeV up to 4 MeV. The behavior of the dissipation energy does not change very much. Can we go to the next slide? So if we plot if we plot the average dissipation energy against the temperature, we can see this linear line with and characterized by the equation in the figure, and we can see that three-dimensional macroscopic friction corresponds to around 9.6, with a temperature of 9.6 MeV. Because of the linear behavior, it is possible to reduce the 3D macroscopic friction from to the targeted to the targeted temperature using this equation. So let me conclude my presentation. The friction tensor for four-dimensional and three-dimensional macroscopic friction are practically similar to each other. However, the rate of rigidity method shows that the difference between four-dimensional and three-dimensional macroscopic friction is quite significant. By understanding the friction tensor, we hope to further develop four-dimensional macroscopic friction. And the relationship between three-dimensional macroscopic friction and temperature is given by this equation. And three-dimensional macroscopic friction is equivalent to a temperature of 9.67 MeV. We propose that the equivalent inversion factor for a given temperature given by this equation. In the future, we hope to refine this estimate and test them again. Them again. I think that's all for my presentation. Thank you.
Sorry to Mark because we will relay the question to you later, I think, once the organizer compile the question. So without further ado, we will proceed with the next presentation by Dr. Azmi Ibrahim, a researcher and expert on the natural drainage system from Agency Nuclear Malaysia. So, Dr. Azmi, the floor is yours. Thank you.
Assalamualaikum and a very good morning. Can you hear my voice?
Ya, dengar.
Can you show my slide? I don't see my slide.
Nampak ada slide.
I don't see my slide.
Tapi kami nampak dan doktor boleh cakap next slide lah. Slide 1, slide 2.
So we already started, right?
Sekarang di title page.
Oh. Wait Saya tak nampak slide saya. Saya buka slide kejap. Alright. Assalamualaikum. Very good morning. How are you, everybody? Can you hear my voice? Okay. Today I will present about rainfall runoff modeling for the basin in Bukit Kelang, Perak. So first of all, my name is Azmi Ibrahim. I'm from Malaysian Nuclear Agency, and there is a member from same agency. This is Dr. Nora Salwa, Nazran Harun, Mr. Muzamil Hashim. Okay, go to the next slide. Okay, first of all, what is the runoff? Runoff is one of the significant hydrologic boundary utilized in the watershed. Reprisal of the surface runoff, which fundamentally relies upon the meteorology, hydrography, geography, topography, soil, and land use design in required for legitimate arranging of the hydraulic structure as just a relief of natural hazard in the region. So now we're just talking about the surface of the study area. Okay, next slide. Okay, this is the study area. The study area is located at Mukim Belanja, Perak. You can see the blue one is the study area, and this is the whole basin in the area, but we just focus on the blue one only. Okay, the basin area include 13.73 kilometers square and perimeter about 19.7 kilometer. And there is Sungai Johan located in the middle of the basin with 2 kilometer length. While Sungai Kledang flow for 6.4 kilometer into Menglembu area before entering Sungai Kita. So they have three river that I mentioned here. Sungai Johan will enter Sungai Kledang will enter Sungai Kita. So the river that includes in this area's study just Sungai Johan. But okay, there are two contributors for this site, which are the residential estate and the industrial. Next slide. Okay, the slide is not clear for me, but I try to read. Now we talk about methodology. First, we have to create the basin from DEM using GIS tool. DEM represents a digital elevation model that shows the elevation data of the site. So we're using GIS tool in hydrological modeling system, HEC HMS, created meteorological model from rainfall data of rain gauge located in the basin using HMS. Okay, and then we have to input time series rainfall data in the HMS, and then create a control model to provide simulation data. Oh, create simulation. I don't see the run model and integrating basin model, meteorological model, and the simulation model. Okay, so and then we have to run in the simulation model and analyze the result. So at the right side of the slide, you can see the flowchart of the HEC HMS model. Next slide. Okay, this is the model. Can you see my slide clear? My slide is not clear here. But I want to try. It's okay. First, we have to create the basin model. So how to create it? In study, the basin model can create using GIS tool in HMS. The digital elevation model DEM was imported. It's better. Okay. Exported into the HMS and processed using GIS tool, and the result is shown above. So from the sub-basin model of the Bukit Kledang, you can see the drainage area or the river basin, and the Johan River located at the middle of the basin, and the basin area including area about 40 kilometers square and perimeter about 20 kilometers. Next slide. Okay, before that we have to choose the correct parameter for this model. So in this study we choose SCS curve number for the model. What is SCS? SCS curve number is a method of measurement for the surface runoff. This parameter is introduced and developed by the US Department of Agriculture. The objective of the curve number is to define the average condition for the purpose of design. In general, if you see the table, the group A table has the highest infiltration rate and a lower runoff capacity, while the group D bottom has the lowest infiltration rate and provide the highest runoff potential. Other groups of the soil fall between them. Okay, next slide. Okay, and then we have to create a meteorological model. This model is one of the primary components of the investigation, which make meteorological limit condition for the basin. This meteorological model can be utilized by various basin model. Result figured by the meteorological model can coordinated with the sub-basin in the basin model, utilize the same of the sub-basin. Okay, next. And then we have to create a control specification. The function of control specification is to monitor the model regarding to the starting and ending simulation at X basic time. The date and timing was important in the model. Next slide. Okay, after we create all the things all the steps that I said before, we can start run and interpret the data. First, we have to evaluate the performance of the model. Okay. For your information, regarding to the limitation of data, we just can create or simulate a LAMS model. Okay, what's LAMS model? LAMS model treat the catchment or basin area as a single homogeneous unit. Average value over the catchment are used, such as a mean soil storage and uniform precipitation amount. In this model, a single runoff output value is measured at the outlet of the sub-basin area. Okay, this model also accurately simulate average runoff condition with short computing time. Yeah, of course, because the limitation of data, so the running process is not too long. All data, including input, output, and parameter, are constant over time and space in the LAMS model. By assuming homogeneity over a sub-basin area, LAMS model loses the spatial resolution of the result. So this model actually just a conceptual models regarding to the limitation of data. Okay. Next. Okay, evolution of rainfall runoff relation. You can see the result obtained describe the peak discharge at study area is 43.4 cubic per second for 30.73 kilometers square of drainage area. The peak discharge occur after 80 hours of rainy days, and the rainfall data are collected over a period of 2 days. On the first day of data collection, there was rain all days. That's why you can see all the high peak discharge, and no rain on the second day of the data collection. Okay, next. The third one, evaluation of rainfall runoff relation. From the point of view of the management of radioactive waste, this result must be seen in the scope of the mitigation of contamination. For a worst case scenario, if the waste disposal cap infiltrated by meteoric rainfall, the surface contamination will be transported by the surface runoff in the disposal area. According to the simulation, the runoff generation in the study area gives a slow rate depending on the relative travel time of basin and also associated with the soil type, land use, multiple storm, and seasonality. That's why you can see the seasonality represent the raining season and not constant rainy days. Next. Okay, conclusion. Based on the present analysis, the rainfall runoff of basin area is likely to be an insignificant source of contamination. Conceptually, the rainfall runoff model for the Bukit Kajang Basin is slow because the soil type in the basin is sandy clay, which is classified as Group D in the soil group that I presented before. While land use for the basin area is a type of forest that provides an interpretation of slow rate of surface water runoff. Okay, next slide. Okay, that's all from me.
Okay, Assalamualaikum and good morning. Thank you for staying online. So we are now moving on to the fourth presentation in this session. The title is Industrial X-ray Computed Tomography Image Reconstruction on Whole Beam Projection. Our presenter is Dr. Muhammad Nur Izwan Ustaq from Agency Nuclear Malaysia. So the floor is yours, Dr. Muhammad Nur Izwan.
Yes. Slide is not very clear. Oh. Okay. Assalamualaikum and very good morning. Today I'm gonna present my work title as Industrial X-ray Computed Tomography Image Reconstruction on Cone Beam with Projection. So I will introduce myself first. My name is Muhammad Nur Izwan bin Ishaq. I'm from Malaysian Nuclear Agency. My work here focus primarily on X-ray computed tomography. Here ada people who help me. Surah Selayah and Muhammad Rabai Syari from Nuclear Agency, and also Ijati Asmil from student from USIM who helped me to do my research work. So next slide. This is my presentation outline. Next slide. Computed tomography, on the abbreviation is CT. It is a non-invasive imaging technique used using X-ray or gamma ray to obtain 2D image or 3D model of the interior of an object based on the concept of data acquisition and image reconstruction. Can you read that word clearly? I can see the word clearly actually, but the X-ray image that we captured are collected by flat panel detector at different angles, and this data are converted into slice. Slice of object from top to the bottom. I will explain later. Those cross-sectional object or sample that we want to scan give visual information of the inner parts of objects hidden from outside. The cone beam reconstruction is the CT image reconstruction of 3D volume from 2D image. 2D image, that is the first image that we captured using X-ray flat panel, which are captured by utilizing 2D X-ray area detector and cone beam geometry consideration. The duration of X-ray scanning is within less than an hour, and maybe 30 minutes for less image. This is achieved with the availability of advanced radiation detector systems or flat panel detector and high-speed computers. The advanced radiation detector is cadmium thallium detector. There are two main concepts in cone beam computed tomography. First, cone beam computed tomography uses this X-ray source and detector, while the sample at the center, the X-ray source will rotate at the center, around the center. Second, the detector and X-ray source rotate around the sample. These are fundamental methods in capturing the 2D image using cone beams, cone-shaped beam. Next slide. The image on the left, the three image on the top on the left, there is the example of image that we can be scanned using CT scanner. And the image on the top right is the example of the use of X-ray, the use of CT in medical field. The image on the left bottom, we can see the view of teeth that are scanned using X-ray CT scanner, and we can see that the 3D image on the bottom right. And also, next slide. Next slide. Here are the we use the Pelham, Davis, and Kress method to approximate X-ray cone-beam reconstruction to reconstruct the image. And this is the algorithm that we use. Here you can see that the object and the arrow. We do data acquisition of the object using flat panel, and you can see that the source and detector rotates around the object, and we acquire many image or projection after scanning the object. N is the number of projection. In the experiment, we use 91 image projection, and then we filter the projection, and lastly we will obtain row-wise filtered projection, and from the row-wise filtered projection, we reconstruct it using reconstruct the image. And next, I want explain about the FDK technique, the algorithm of the FDK technique, but you can refer to the Torsten and Buzuk book, which he explained in detail about the technique. You can see the reference section for that. And Torsten and Buzuk, the book of by Torsten and Buzuk, titled as Computed Tomography. Here, the study that we conduct here, we use the cylinder type of phantom with a diameter of 129 millimeters and 16 holes of different size, from the smallest to the largest hole. The sample is a custom phantom with holes which is made of polyethylene. Phantom with different diameter size of holes is useful for resolution study in the next phase. We usually use phantom in situ for calibration purpose. In this study, the image consists of 91 two-dimensional projection, which the intervals were 2 degrees for each projection. That is from 0 degree, 2 degree, and 4 degree, and so on. Next slide. Here is our setup for the X-ray experiment. The experiment was conducted using the phantom cylinder sample put on a rotating table on with 70 centimeter of distance between the X-ray tube, is our source for radiation, and the object, and 85 centimeter distance between X-ray source and flat panel detector. The angle of rotation taken at every 2 degrees until 180 degrees with constant parameter of 25 kilovolt, 2 milliampere, and 1 FOC, or the focal ratio of the X-ray. Before the experiment was started, a few parameters such as voltage, current, and FOC was tested to obtain clear image of the phantom cylinder, which takes about an hour or more. All images produced by the X-ray are compiled in a file to be reconstructed into city image. Here you can see our setup in the picture. Next slide. This is our flat panel detector on the left, and the software we use to acquire the image that we obtain from flat panel detectors. The data on the image actually the intensity of X-ray that is reaching the flat panel board. And we acquired 91 image on the IIP console software. Next slide. This explanation for our flat panel detector. Image acquisition is performed using Ryan's 1012 WGB flat panel detector. This flat panel detector is made of amorphous silicon with TFT with total pixel matrix at 2560 times 2048 pixel. The flat panel detector converts X-ray energy into electrical signals for digitization. It consists of film of cesium iodide scintillator crystals that is cast onto a matrix of photographic detectors made of amorphous silicon. The scintillator converts the X-ray energy into light. A number of correction algorithms are applied to the raw projection data that is in our acquired image before they are reconstructed into a 3D stack. The afterglow correction is special to the cesium iodide based detectors because cesium iodide is a slow scintillator, and artifacts may arise from residual glow from the previous projection image. The advantage of using flat panel detector are high spatial resolution, real-time fluoroscopy, volumetric coverage in one direction, and dynamic imaging. Image acquisition, control, and processing is done by IIP console software, and it connects to flat panel detector to acquire digital image. Next slide. Here is the you can see the user interface for Octopus imaging software. The software that we use to reconstruct 3D image from our raw projection that we acquired from flat panel detector. Next slide. X-ray scan will provide image output that can be processed into cyanogram. First, we will get cyanogram by using the Octopus imaging software. And cyanogram is obtained by tracking profile data from all projection angles. That is from the top to the bottom. Top first, and we get the line of the image from the top, and we stack for all projection data. Then we will reconstruct it to form two-dimension image by using Octopus software. The parameters in the image can be adjusted in order to get clearer image. Perhaps our parameters that we put in can be in error. That's for example, the sample source object distance and source detector distance. Perhaps there is an error in our measurement. Can I see the previous slide? this this is as you can see, this image of atom cylinder that we acquired using flat panel detector. First image is at 0 degree, and then we get the image for every 2 degrees until 180 degrees. Next slide. Here is the cyanogram we got by stacking the upper pixel of the flat panel image for all 91 image. It's, the height of the pixel is 91 pixel. So that's the image from the top of the cylinder to the bottom of the cylinder. Next image, next slide. The concept that is useful to use when considering city reconstruction is the cyanogram, which is simply the 2D array of data containing the projections. Typically, we collect the projection using a hypothetical parallel beam scanning arrangement using f as the angular parameter and x as the distance along the projection direction. We refer to f as plane representation of the data as the cyanogram. CT involves several steps in producing real-time slice of image, which comes from the application of the several mathematical theoretical concepts behind it. This concept is quite important for academicians and also researchers since cyanogram is capable in explaining the beautiful part of random transform and line integral application in producing the image of an object. The quality of the produced image so can be analyzed based on the generated cyanogram. Next slide. Here, as you can see, there's a 2D reconstruction of the phantom cylinder, and you can see all the holes, the cylinder and the holes from 754 pixel and the height to 1237 pixel. Next slide. This is the image from the top. There is from the top you can see the image is not full. And the bottom picture is the bottom of the cylinder. Next slide. There were 669 slice image obtained for phantom cylinder from the height of 649 pixel to 1000 and 1317 pixel. Phantom cylinder can be viewed clearly from 695 pixel to 1000 and 1248 pixel. The rest of image can be reconstructed clearly because there are other caused by comb beam effects or tilting. Next, ring filter algorithm in autofocus imaging is applied to correct for systematic pixel deviation, which would otherwise result in ring artifacts in the reconstructed slice. It's a ring artifact we can see from the first time we reconstruct the image, and then we apply the correction, and we can see the image clearly. The effects of air and noise can be observed in all of these slice figures. This might be caused by unfiltered X-ray beams or unsuitable voltage applied to X-ray tube. Other artifacts can be observed around the holes inside the cylinder phantom shape. All holes are reconstructed at the exact place as they should be, but some shapes are not exactly circular. Some holes form near triangular shape or deformed shape. Next slide. Here's the 3D models and reconstructed by stacking all the slice image from the top to the bottom. There is image from the view from the top and from the side. As you can see, there is noise from the image. Next slide. Based on the conclusion for this experiment is based on the results, reconstruction of combined computed tomography image using Octopus imaging software for 91 numbers of projection is successful with limited precision. However, with a limited number of computer resource and projection, the 3D image of phantoms seen not in a clear view. Therefore, it is recommended that further research can be conducted in applying a higher number of projections for better image reconstruction. The experiment also needs to be repeated by changing few parameters like the center of rotation, X-ray tube voltage, and additivants like aluminum and copper to obtain clearer view for the sample. Yes, right. This is my reference for this experiment. Next slide. Thank you for listening for my presentation today.
Okay, Assalamualaikum and good afternoon. Thank you for staying online. Welcome back to iNuSTEC 2020 session 2A. We are now at paper number 5, titled Quantified Needs and Requirements in Pre-Preparatory Outline Functional Specification in Malaysia. New Research Reactor Pre-Feasibility Study. So our esteemed speaker is Dr. Mazleha Maskin, my dear friend from Agency Nuclear Malaysia. She obtained her PhD in nuclear engineering under supervision of Dr. Faisal in UKM. She is one of the few experts in PAC in Malaysia, and she completed her master's in Korea, KAIS, under the KAIS Keynes program. So we are honored to have you, Puan Mazleha. So the floor is yours. So all the best.
Hello.
Dengar.
Okay. Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Thank you, Mr. Chairman, my dear friend also, Dr. Shukri. So the topic is, of course, quantified needs and requirements in pre-preparatory outline functional specification for Malaysia New Research Reactor Pre-Feasibility Study. Okay, I admit that the title is longer, but I can assure you that the contents of this presentation will be very simple and straightforward. So the theme of this pre-feasibility study for a new nuclear research reactor is consists of Ms. Nurhayati Ramli, Mr. Muhammad Khairul Arif, Dr. Julia Abdul Karim, and me myself. All of us are from the Reactor Technology Center, Technical Services Division, Malaysia Nuclear Agency. Next, please. Next, please. Yeah. Okay, so these are the outline of this presentation. I will start with introduction and then follow with objective, objective, methodology, scope of work, result and discussion, and then conclusions. So some introduction of our reactor. We have been operated since 28 June 1992, and that is 38 years of safe operation. We don't have any major safety issues. And the name of our research reactor is Trigger Mark II. The model of our reactor is Trigger Mark II, and the name of our reactor is Reactor Trigger Puspati, which Puspati stands for Pusat Penyelidikan Atom Tun Dr. Ismail. So under here, I put a bibliography, IAEA 2018, which in this IAEA book, it stated that a lifespan of a nuclear research reactor is between 30 to 40 years. And of course, in this book also, it stated clearly that a nuclear research reactor also can be extended. The lifespan can be extended to 50 to 60 years. But I just want to highlight that we have been 38 years of a safe operation, and we are thinking about to have a new research reactor. And for this specific presentation, we want to justify how our reactor, how we utilize our reactor both in operation, utilization, and also in educational and training. Next slide, please. So the objective of this presentation is, of course, to present an adequate justification so that we can get a new nuclear research reactor for Malaysia both in quantification needs and also requirements. Next, please. So we have the methodology. We are trying to assess 5 topics of feasibility, and the topics are as per on your screen, which is radioisotope feasibility, experimental feasibility, fuel feasibility, nuclear safety feasibility, and also educational and training feasibility. Next, please. So the scope of work of this presentation, we only use our operational data, none other, just our operational data, and all of the operational data we took from reactor trigger Puspati activities records, especially in operation and also utilization of our irradiation facilities, and finally the education and training feasibility. For your information, we didn't take into account the supply and demand for radioisotopes, both from hospitals or industries. Next, please. So on your screen is just an overview of RTP operational data. As per mentioned, this is just a straightforward presentation and a very simple presentation. So this is just a chart of our operational data, consists from 2001 until to 2020. The red colored bar chart is our how many energy has been released. Meanwhile, the blue line chart is the operating hour, how long we have been operating our reactor. So next, please. So the first assessment, the first topic assessment is radioisotope feasibility. So I only presenting the current radioisotope that recently had been irradiated in our reactor. So as you can see on your screen, the most irradiated radioisotope is samarium, which is used for medical purposes, especially for bone cancer palliative care. And you can see that we have two bars, the orange one and also the blue one. The orange is the one that we irradiated, the samples that we irradiated in dry tube, DT. You can see at the legend up there. And then for the blue one is the one that we irradiated in our central timber, CT. So here, for the statistic of the samarium, I only just show the statistic of the samarium here, which you can see that we have quite a numbers of radioisotope being irradiated, especially this samarium in 2018 and also slowing down in 2019. But in 2020, we have lost almost 6 months due to movement control order. So we only managed to irradiate one sample of samarium. Next, please. So for the second assessment is experimental feasibility. But sorry, because I didn't what is RR, what is PTR. Okay, basically what you see on your screen is just the irradiation facility that we have in our reactor. RR stands for rotary rack. And for rotary rack we have 40 hole for samples, and then we have PTS, which stands for pneumatic transfer system, and then we have NUR, neutron radiography. SANS, small angle neutron scattering. TC stands for thermal column. CT stands for central timber. DT stands for dry tube. Here is the one that we irradiate the radioisotope, especially for samarium for the medical purposes. And then we have IC, can't remember, irradiation channel. And then we have 4 beam port. Beam port number 1, beam port number 2, beam port number 3, and also beam port number 4. So as you can see, because rotary rack, the RR, has 40, you can occupy up to 40 times 2, up and down, 80 samples. So you can see that the numbers, the statistic numbers of samples irradiated in RR and also PTS is quite high, which is almost like 1,000 to 2,000 per year in average in RR. And then for DT, for the dry tube, you can see that it's almost approximately 15 to 20 numbers of samples, average samples irradiated in dry tube. So next, please. So what you see is on the screen is just a plot of the figures that I just shown you in the previous slide. We have two parts here, the upper part chart and also the bottom part chart. The upper part chart is consists of only rotary rack and also PTS, pneumatic transfer system, and also a blue line which is showing you how long we have been the operating hours of our reactor according to the years. And then for the bottom part of the chart, we have other of the other facilities, not including RR and PTS. So if you can see, I just want to show you for 2019, even though you can, please look at the bottom part chart. If you look at that bottom part chart at 2019, you can see that there is not so many samples being irradiated in that year. But please look at the blue line chart, which represent the operating hours. So it is showing you that even though we have small numbers of samples being irradiated, but that samples has been irradiated for a quite longer time. And for your information, like samarium, we operate the reactor at least 18 hours to get the dose that we want. So next, please. So what you see, sorry. And this is an evaluation for the third topic, which is fuel feasibility. And just look at the blue line. So the blue line is actually the burn up of our core. So up to now, we have configuring our reactor up to 15 cores, and we are currently at core 15. So the orange line is just the accumulated burn up. And for your information, if you look at the core 11, core 12, and core 13, it looks like the burnout is increasing. No, actually it's not increasing, but the burnout release of each core is proportionate to the duration of the core. Example for core 11, we have been, it's almost 1 year, like 57 months. No, 4 years. And then for core 12, it's only 1 year. Meanwhile, for core 13, it's only for 11 months. And why it is a very short time for all these three cores? Because in core 12, we did some, not amendment, but we inserted a new control rod inside the core, and then we reconfigure the core to become core 13. Meanwhile, core 13, we inserted a new IFE fuel element, instrumented fuel element. So next slide. And the fourth topic for assessment, feasibility assessment is on nuclear safety, but not really a nuclear safety. It is more on the modification of what we have done in our reactor. And this modification is basically consists of refurbishment, replacement, and also upgrading of our reactor. So this list was taken from our new safety analysis report that was released in 2020. And out of 21 modification that we have done, I just listed only 6 here. And the recent modification that we did is at number 1, which is refurbishment of our stack monitoring system, which was done in December 2019. And then back in March 2016, we did quite a major modification, which is a replacement of cooling tower and also fission chambers. Again, in December 2013, we changed our console from analog to digital, and also known as REDIX, Reactor Digital Instrumentation and Control System, which was a joint venture and collaboration project with KERI, the Korean Atomic Energy Research Institute. Back in September 2009, we did also a major upgrading of our primary cooling system. And in December 2005, again, so this is the first time we replaced our stack monitoring system, meaning that for the whole 38 years of operation, we have replacing and refurbishing our stack monitoring system twice. What I want to show you here is that it's like having an old car. You have to refurbish, remodify, renew some parts and components. So the same with our reactor. In order for us to maintain the operation, the safety operation, the safety of operation of our reactor, we need to change and modify some system and some components. Next slide, please. So this is the last assessment, feasibility assessment, which is educational and training. So for your information, we have been conducting ENT activities for some universities, local and also overseas. And also we did conduct some workshop, especially at the number 4 and number 5 NSIP and also RSIP. And we also did the training courses for follow-up training course, which is a collaboration with Japan, and it had been ongoing since 2013. So, and as you can see, we are providing ENT activities to our local universities, especially for University Technology Malaysia, because they have this bachelor degree in nuclear engineering, and one of the requirements for them to graduate is to attend this course, the one that we have here in our reactor. We also provided some experiments to Unit 10, University Tenaga Nasional. And in 2016 and 2018, we did also provide some classes to Sudan University of Science and Technology. So next, please. So this chart on your screen right now is just the numbers of participants for each university and for each workshop that we had organized. So basically for UTM, usually every year we will get 31 to 30 students. Unit 10 also almost the same numbers. The same goes to Sudan. And for FTC, fixed participant is around 20 participants, but in 2017 we drag the 2018 participant into 2017. That's why you can see the peak here in 2017 and 2019, which we have 40 participants for each year. And next, please. So what you see on the screen is the list of experiments that we can offer, that we provide. So I also put a sign there for UTM what kind of experiment they want, and then for Unit 10 they want this experiment. I just put a slash there, meaning that they want this experiment and not the other experiment. So basically, we provided these experiments, and we have quite a numbers of experts in doing and conducting all these experiments. Next slide, please. And then, meanwhile, for this slide, it is showing you the list of lectures that we can provide. So the same with the universities, I also put a slash there. Like UTM, we gave them all for the first four: reactor physics, thermohydraulic, instrumentation and control, and probability safety assessment. So for your information, all these lectures are based on our reactor. Not just general information, but specifically on our reactor. So next slide, please. And this is my final slide, which is the conclusion. So basically, I just put there, yes, it is a strong justification that we really need a new research reactor, because at the same time, it will increase interest among researchers. And they can utilize, especially utilizing our irradiation facilities, especially at dry tube, central timber, and also at our beam part. And conclusion number 2 is by enhancing the utilization with a new reactor, we can, of course, fulfill the needs of utilization. Not just fulfill the needs of utilization, but also to strengthen expertise in nuclear for all Malaysian. So that is all from me. Thank you very much.
Right.
Okay, Assalamualaikum and good afternoon. Thank you for staying online. So, thank you for Dr. Mazleha for a very kind presentation before. So, we are now moving on to paper number 6 in session 2A. So, the title is the efficiency of transformer for high voltage performance in radiation detection. So, the presenter is Puan Nur Arimaswati Abdullah, researcher from Nuclear Agency Nuclear Malaysia. So I wish I can talk more about Puan Arimaswati, but I'll let you introduce yourself later, okay, Puan? So that's all from me. So thank you. So the floor is yours, Puan.
Okay, thank you. Thank you, Mr. Chairman, Dr. Shukriya here. Assalamualaikum and everybody. Actually, my presentation changed to the new one. Sorry for late inform to Secretariat. So my presentation entitled actually power consumption comparison in 3 experimental circuits for radiation detection. Actually, this is a small project come from one of our proposal to produce a low-cost survey meter in Nuclear Malaysia. This low-cost survey meter planning to be used in school or any simple training regarding the contamination from gamma ray. And my presentation will share the flow of how to build or assemble one of the main circuit in radiation detector, or we call also giga counter. And then I will share the result in comparison between the circuits in terms of voltage, current, and also power consumption. And as a normal presentation, I will start with the introduction and then continue with objectives, followed by methodology, and finally the result. Next. Okay. As we know, the safety issue is most common important issue when it comes to the every kind workplace, including the radiation. We know that radiation cannot be seen or felt for low level especially, and for that, radiation detection device is one of the most essential topic when it comes to radiation, especially in either in non-ionizing or ionizing itself. For that, I have find a few research or study have been done in both fields. Here, I just pick a few to share with all of you. And one of that is the researcher investigate the high energy ionizing radiation phenomena that emitted by the electrical discharge, and also some paper share the voltage transformer that have been done with extremely low frequency electromagnetic radiation to investigate the effect of exposing it to the selected student. And the third one, actually, I miscategorize the point. Actually, scintillation detector is under the ionizing detector. So this paper share they try to produce the ideal scintillation detector. For ionizing detector, I focus on giga counters only. Actually, a few studies have been done up to recent years. There are review study on insulation capacity on GM tube itself in 2018, and some study of stability of high voltage itself in 2018. Okay, next. Okay, and also they use the Monte Carlo in modeling of gamma ray stopping efficiency in GM tube, and also stimulating gamma ray stopping efficiency in 2011. And also we can find that they also study the voltage dependent pulse analysis using correlation technique. And in 2016, they have patent on improvement in manufacturing and halogen quench of GM tube itself. So while giga counter is still available in the market, even it is the oldest detector device globally, and normally some people also know still question why is it visible until now. First, it is because robust in most environment, and second, simpler design, and third, compared to other detector, has a low cost. And also for low level contamination compared to ion chamber, GM tube is more sensitive. Okay, next. Okay, therefore, our objective of the project is to develop a stable high voltage circuit to be used in low cost survey meter. Therefore, we propose 3 model circuit of high voltage that will assemble, and power consumption of each circuit will analyze, and the stable high voltage will be used in the survey meter. Actually, we have 4 model circuit, but since we not enough the component and the probe, so we decide only for 3 model circuits only to be compared. So next. Okay, these are the block diagram of Giga counter. As we know, my point is to in high voltage of the Giga counter. In a Giga counter, there are few parts that contribute to be part of the Giga counter. They are high voltage GM tube, signal processing, and microcontroller. The display and the button is function as to show the measurement or reading, and button to normally to start and stop of the system. And buzzer is normally to indicate the contamination level by sound. Meanwhile, voltage regulator to regulate the power supply into 5 volt. Normally, it comes from 6 or 9 volt battery. For GM tube, it is device to use the detection and measurement of all type of radiation. Normally, they use to alpha, beta, and gamma, but our focus is for gamma only. And basically, it consists of a pair of electrodes surrounded by a gas and filled with an inert gas such as helium, either neon or argon at low pressure. And when the high voltage applied to the GM tube will activate to produce the pulse as a signal of radiation detected. And normal for our case, we use the LND 7121, which we need to produce the HV between 400 to 600 volt. And the function of signal processing is normally to generate the make the pulse come out from the GM tube to be smooth, so can be read by a microcontroller. And the signal processing also will stretch and reshape the pulse into acceptable pulse, and this acceptable pulse will counted by microcontroller. And the microcontroller also, the function is to overcome to dead time in GM tube. For LND 7121, the dead time is 90 microsecond minimum at least. Next slide, please. Okay, these 2 of 3 circuits that has been used. The third circuit will show at the next slide. Actually, the circuit for circuit 1 and circuit 2 actually same, but a few things component is different. The different in circuit 1 and circuit 2 is coils and a few other components. In circuit 1, the primary coil is only 1, and the circuit 2, the primary coil is 2. So the total up for circuit 2 is 3 coil. Other component used is 5-5 timer. The 5-5 timer is to produce the waveform with additional of RC externally. So you can see the RC is 210 resistor and 1 microfarad capacitor. So in circuit 2, we use 4013 D-type flip-flop. The D-type flip-flop changes the value according to the inputs, the data inputs or the set inputs and the reset inputs. They store the value at the output indefinitely unless the value is changed by manipulating the inputs. If you don't change the inputs, then the value at the output stay the same. We use also TIP 122 is NPN transistor for low speed switching. Then okay, the next. Okay, this is the third circuit. This circuit we didn't use a transformer, but we use the inductor. The inductor is to store the magnetic flux, and also we use the variable resistor. As shown by VR1 20K. So this variable resistor is to manipulate the resistance so that the output produce required the required voltage. By reducing the resistance, the voltage will be increasing or otherwise. Okay. Okay, these are the flow of the process we produce the HV circuit, HV board, and we of course we assemble on the breadboard the component, and at the same time also wind the transformer. The transformer is limited size, only RM8 size, and we winded it manually. So the winding scheme we use the A type or U type. Actually, there are 4 type of winding: U type, Z type, sectional, and deep and bank. But for this case, we use only U type, and because also not enough transformer, we use only type 1 type. And all components were soldered on straight board after we finish and testing the circuit with the transformer. But we not on PCB board because we not enough budget for that time. So okay. Okay, next is a result. Okay. For this, the result for the circuit one. As you can see, the configuration for transformer is increasing by 10 up to 50 for a primary coil. But the secondary coil, we wound up to the maximum the bobbin can accept. And there are different, you can see different winding or at the secondary because it's depend on how you wind at the bobbin. So can be seen the HV and the current fluctuate for this circuit not proportional. The 10 winded coil have no result, but for 20 coil produce 300 volt, and it jumped to 600 volt for the 30 winded coil. And as you can see, for the rest 4 below, we winded 50 for the primary, and we changed the secondary actually to reduce the voltage in between 400 and 600, but we failed to get the result. Okay, this circuit 2 result. For circuit 2, same as circuit 1, but increasing by 5. And for the circuit 2, as mentioned, for primary coil, we have two coil. And as soon actually we put the power supply, the power remain a few minutes, and then it dropped between 0 to 290 volts. And the power also, as I show here, is starting power before it dropped. Okay, the next. Okay, this is the result for circuitry. As you can see, the circuitry, we don't have a transformer configuration, but we use the resistor to manipulate the output. As you can see, when we reduce the resistance, the HV value start increasing, but when we reduce below than 3.8 ohm resistor, the HV value remain as 455 volt. And as you can see, the current also start increasing when the HV value increase. Okay, next. Okay. These are the figure plotted for each circuit, and as we can see, the figure for circuit 1 and circuit 2 is fluctuate, and for the circuitry, most of for the circuitry is proportional, and it stopped at 455 volts. But however, you can see the figure 3 power consumption, the power consumption for circuit 3 is highest than the others. So the right axis for figure 2 and figure 3 is for circuit 2. So you can see circuit 2 is much more higher than the others. Okay, next please. Okay, in the conclusion, all the currents and high voltage of the circuit were recorded and plotted as shown in table 1 and table 1 to 3 and figure 1 to 3. The voltage is not only depend on coil, but also actually the magnetic flux density, current, and area of coil, as well as voltage, each voltage turn. Then based on the data collected, the model 3 is applicable for LND 7121, and for that is more stable, producing high voltage, even though the power consumption for circuit 3 is the higher than the others. So therefore, we use decide the circuit 3 to for the project. And next. Okay, this one is only the knowledge for FYGS of Unit 10 to sponsor me in this program and the reference. Okay, next, I think that is all. Okay, thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon. Thank you. Thank you for staying online. And we are now finally at presenter number 8, the last paper for session 2A. So the paper is titled The Multi-Pronged Core Power Control Strategy for Reactor Trigger Puspati. And our esteemed presenter is Encik Muhammad Sabri Binhat, a researcher from Agency Nuclear Malaysia. He has the Master of Science in Mechatronics, I think, if I'm not mistaken, and is very experienced in the power control. So without further ado, I give the floor to Encik Sabri. So all the best.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and very good afternoon. Thank you, Mr. Chairman, Dr. Shukri. First, I introduce myself. My name is Muhammad Sabri. I'm from Malaysia Nuclear Agency. This project is collaboration between MNA and also UTM. So today I will present a multi-pronged core power control strategy for reactor 3 Puspati. Next slide, please. So this is the outline my presentation. So next slide, please. In general, when we talk about nuclear reactor, actually we are referring either is a research reactor or power reactor. So both type of reactor, they have a content of reactor core, and inside of reactor core they have nuclear fission process. So in terms of safety and effective operation and utilization, we need to improve from time to time. So for this project, we are focused more on the research reactor. Next slide, please. This is our RTP, our research reactor. So already introduced by previous presenter is Dr. Mazleha. So I need to skip this slide. So next, please. See the next slide, please. Okay, in the reactor, how we control the reactor, we need to withdraw the control rod. So the control rod contain the boron carbide. So during shutdown, all control rod inside the core, and when we try to critical or try to increase the power, we need to withdraw the control by the rule is one control rod can be withdraw at one time. So until we are try to get the power. So next slide, please. This is a close view of our reactor core picture. So they have 127 number of hole. So now we have 111 few element we can inside the reactor core. So in the picture we can see there are 4 control rod and also surrounding by the graphite reflector. Next slide, please. Next slide. Okay, in the reactor we have a lot of parameter we need to control and monitor. For this research, we are focused only the power parameter. So to control the power, we have currently we have a power control system algorithm. We call it FCA, feedback control algorithm. So this is the picture. At the left side, they have picture our INC, instrumentation control console, located at our control room. Next slide, please. So the FCA control algorithm, you can see in the slide is the detail of the block diagram. So the simplified model we can see in the next slide. Next slide. Okay. From the reactor core, we have a neutron or our neutron detector, or we call it fission chamber, to measure the reactor power, and it's measured from our NMS, neutron monitoring system. This represent the current value, the current power. We will compare with the power demand what the desired power. So based on these two error, based on this different, they will fit into the controller. So the first constraint is to make sure the reactor rate of power power chain rate constraint not be more than 12.5% per second. So the controller will process based on this error, and to generate the output is the velocity. So the velocity for the current control rod should be not more than 2 mm per second. And this control will insert the reactivity insertion to the core, so to increase the power. So during operation, all the safety parameter we need to fulfill, such as not overpower than 110%, also, and rate of power change not more than 33.3%. And you can see they have a multiple constraint. There's rate of power change and also control speed. Next slide, please. This in the inside you can see the real data from our RTP. So we can see they have the blue line show the power demand, and the red line is show the response, the tracking power from low power to desired power is 75%. It takes about 2 minutes, around 120 seconds to reach the desired power. So the yellow, the actuation signal is the actuation signal to control drive mechanism. You can see before at low power they have very fluctuate signal due to reactor not critical yet. So until they get the power demand and the fluctuation signal is less. Next slide, please. During at the steady state, we can see the chattering error. We call this chattering error. The maximum and the minimum value of reactor power is about 2%. It's still acceptable value, but for this system we try to improve it, because the actuation signal if too fluctuate, or it can represent an aggressive signal, maybe can increase the probability to damage the control rod drive mechanism. So next slide, please. Okay, based on the two problem, based on during transition, the control surface yes take a longer time to reach the power, and also during the steady state, they try to the current FCA is suffer to regulate the power based on the control rod at the reactor. So we try to minimize these two problems, and then based on our previous study, we have proposed a new the improvement method based on combination based on power chain rate constraint, based on control rod selection algorithm, and also the control speed design. So next slide, please. Okay. In this slide, they show three work we have done. We have proposed control speed, control selection algorithm, and the control speed design based on the different saturation model, and also what the optimum value for the speed for operation. And also last iNuSTEC 2019, we have proposed a fuzzy logic for power chain rate constraint. So based on these three works, they are individually is not integrate. They have still not optimized. So in this study, we try to combine two or all type of this modification component and try to investigate the effectiveness. Can we improve the current performance or not? Okay, next slide. Then this is the objective to optimize the power tracking performance or RTP by using multi-pronged strategy. Next slide. So the methodology, we need to model the reactor first by using simulation. Then we compare with the real data. After we certify the model, we validate the model, so we can go to the next stage to design the controller. So design controller based on the previous work is 9-11 is the 3 paper that already shown in last previous slide. And then we try to investigate the effect based on the combination 2 of 3 improvement. Then try to compare with the existing FCA, and if the result is expected, we can publish and write paper. If not, we need to do a design again until we certify the result. Okay, next slide. The model will on the RTP will be using analytical method based on physics. And next slide. So next slide. And based on literature, we can define the nonlinear model based on neutronic point kinetic model and also the thermodynamic and the reactivity model as shown in the screen. So from this nonlinear model, we can represent to in the linearized form, such as a transfer function or state space. And next slide, please. And based on comparison between simulation model and also the experimental, we show about 97% best fit. So we can say this is a good model. This model is combination between RTP model and also the FCA controller. Next slide. Next slide, please. Okay. To design the new controller, we need to take into account about a predetermined the safety design. So only the difference is the control speed. We need to increase it from 2 to 3 because they have not optimum value and also they have saturate. We try to improve for the new control speed design based on this value 3 mm. And the others for safety parameter and for first constraint about control speed design, control power chain rate constraint still maintained. Next slide. Okay, for the first component, is a control rod selection algorithm. Is the conventional is we draw control based on the rod position. We try to balance the control rod based on the rod position until we achieve the power. So the model we can see is the CCRCA model in the frequency domain. You can see here, and also the result show in the line, the red lines. And we try to propose a new based on instead of using a rod position, we use the highest reactivity rod first is by using regulating rod approach. We call it SCAR, single control rod absorbing rod. We can improve the performance from the red to become the green one. The green one is a new based on the CR's new control rod selection algorithm. Next slide. This is the first component, and the second one we try to study to investigate about the type of the saturation model and also the optimum control speed to produce a good or to produce good reactivity insertion rate value in order to have a better performance. So the saturation model, for this paper, we are focused on only hard saturation, and they have others like soft model and also CMOD model. We can refer in this paper in the progress in nuclear energy. And next slide, please. And the third one component we approach based on the previous work is application of fuzzy logic for control speed for power chain rate constraint. So this the fuzzy logic based on the linear membership function you can see in the right side. So this equation we will penalize the control rod speed design calculated by controller. So in order to have a better drivability to add the CRDM, and also we try to reduce the sensitivity during operation for the control rod mechanism. Okay, next slide. Okay, the combination of the three of an improvement model, we can unify into the single model. And from this from the slide, you can see a combination of three model and from three previous work into a single unified model. And based on the combination of 2 and 3 model, we try to investigate the effectiveness of this proposed method for this project. Okay, next slide. From the previous slide, they have we can categorize about 8 type of reactor, including the current FCA in the red lines, we can see power will increase from 10% to 75% is nominal power operation. So the B, C, and D is the single approach based on the previous works, and it's not optimized. We need to introduce a multiple approach such E, F, G, and H. And from this figure, it's very difficult to see. We need to tabulate in the table on the numerical values. So next slide. And these are the actuation signal at the control rod mechanism. All type of controller that we test it is produce a smooth signal and don't show any aggressive. This means it's a very safe actuation signal, in order to test to the real plant. Okay, next slide, please. Based on the two previous graphs, we can tabulate in this table. And the original is about, previous I've said, is about 2 minutes 120 seconds, the certain time. So based on the new single prompts control strategy, based on only one improvement model, B, C, and D, the new control selection algorithm based on a different pattern on B, they improve. And they have show almost zero overshoot, and also the chatting error very significant improvement. And also the workload is about 60 mm per second. They take a minimum workload in order to have the power demand. So in terms of the multi-pronged strategy, the E and H are the better. So E is combination on the control rod selection algorithm and also the increase the speed. That's why they have on par with the B type in terms of the setting time, also the zero overshoot, and also the chatting error, and workload is less than, it's about 60. And the difference between E and H is about the control surface area, and because H has introduced a new fuzzy logic, a new PCRC. They are trying to reduce the sensitivity. That's why they have not good in terms of during transition, but it's better during the steady state. And we can see the chatting error and also the settling time actually better than E. The next slide. Based on this table, we can profiling and analyze based on the criteria performance that we define in this paper based on small spectral time, fast response, smoothness, control surface during transition, and the actuation signal, and steady state error, and also the high energy release. So from this, we can say multi-pronged control strategy can actually improve, can provide better in terms of the fast response and control smooth transition, surface during transition, and also provide the high energy. Actually, we utilize the energy from the reactor, so to irradiate the sample. So next slide. Okay, for the next future work, we try to introduce a different structure. Currently, we are only scope limited for the minimum major chain of the FCA. So maybe in the future, we try to introduce a new controller. We try to tuning the controller and also introduce the new signal filter. Maybe we can provide better result. Okay, next slide. For conclusion for this paper, so the study of multi-pronged control strategy has been presented. We provide a greater safety with more realistic design towards solving practical problem. We can say this optimization problem, and then instead of using a single prompts like new control selection algorithm, new control speed design, also new power chain rate constraint, we can use a multi-pronged control strategy as an alternative to offer a wide solution in optimizing the core power control performance. And the significant finding from this research for the paper, we are able to provide better understanding about the relationship between the element, between the three prongs element, in order to have a better result. And insight for new future for this for new step what we need to do based on this result. Okay, next slide. So in order to Minister of Education to for supported for this grant FIGS, and from team from UTM, from especially Dr. Nuradila and the team, and also from National Nuclear Agency under the MOSTI. Thank you very much. And next is the reference for this paper project, and also that's all. Next. Yes, thank you. If any question.
Thank you, Cik Sabri. Thank you so much for your kind presentation. I'm sorry we don't know how we can compile the question for now, but for the time being, thank you, and we have to let you go. So we will come back to you when we have the question. Okay, guys, that's the end of the session 2A. Thank you so much for staying online, and thank you for joining us on YouTube and also on WebEx. So we truly appreciate your time, and we appreciate your passive participation for now. And that's the end of our session, and I would like to announce that we are going to hold a Kahoot competition. So that's prize for Kahoot. It's not only trivia question. There's a prize for it. So we will announce and we will give up the prize online transfer on Thursday. So on Kahoot, so please go to Kahoot, and the room number for our iNuSTEC Kahoot quiz is 6283496. So again, I repeat, we are holding a Kahoot quiz for iNuSTEC 2020. There's a prize for it that we will announce this Thursday. It's a cash prize. If you win the Kahoot quiz, there are a couple. There'll be 10 prizes. We will transfer the money to you cash. And to join the Kahoot quiz online, here is the room number: 6283496. Again, 6283496. Okay, so I think the Secretariat will also post the number on the holding screen. So that's all for now. Thank you so much. All the best. Okay, we will resume the conference at 2:15 p.m. later today. Thank you.
But since x0 is sparse, only several elements have non-zero values. The rest are zeros. Therefore, the image can be
poster is on Gigamolar detector dataset for simulation.
Hi, Assalamualaikum and good morning, Malaysia. My name is Linda Anwar. I am a nuclear engineering PhD student at Texas A&M University. Today, I am going to talk about my PhD research, which is on the application of non-negative least squares to image gamma source for nuclear security. Let me start first with the motivation of this research. Close to 3,500 incidents have been reported in the span of 25 years involving radioactive and nuclear material trafficking. So this is an average of about 140 incidents per year. So though some incidents were actually found to be harmless, it is also very concerning to know that these actually happened. So there's a high attraction for radiological sources to construct radiological dispersal devices, also known as dirty bombs. And this is one of the reasons why border crossings and shipping ports are equipped with monitoring systems. But secondary monitoring systems would be useful to verify the alarm set off by the primary monitoring system. It will also help personnel on duty to make decisions on how to handle the suspected radioactive material. So in this research, we are interested in designing an imaging system specifically for gamma source that acts as a secondary monitoring system. So the research objective is to develop a design concept for imaging gamma sources using compressed sensing principles. The resulting system is expected to localize the image radioactive source and provide its shape information. So this can be achieved by first conceptualizing the gamma imaging system and then design an initial proof of concept using Monte Carlo simulations. We would then build the apparatus based on the simulation results and then do testing and try to match the experimental results and simulation results. And based on these, we would then modify the simulation model or the experimental design to validate the results. And finally, we would then propose an improved design or technique for the gamma source imaging system. Compressed sensing has gained popularity through its success in improving signal processing efficiency in various applications such as facial recognition, photography, network management, radio astronomy, and so on. So I like to use the concept of image compression as the starting point to understand compressed sensing. So how does image compression work in general? So we can apply one of the popular methods called transform coding to an image X, which will turn X into a sparse or compressible representations of signals. So what is sparse, you ask? Sparse means that for a signal of length n, we can represent it with only k non-zero coefficients, and k is way less than n. And compressible representation means that the signal is well approximated by a signal with only k non-zero coefficients. So therefore, let's say we have an original image of a cute little kitten here, X. We can perform transform coding on it, and this will give a different vector X naught. So this X naught is now the sparse version of X. So they are literally the same thing, only represented differently. And almost every element in X is non-zero. As you can see, there is a lot of different colors for each pixel. But since X naught is sparse, only several elements have non-zero values. The rest are zeros. Therefore, the image can be stored more efficiently by only saving the non-zero coefficients and also the locations of these non-zero coefficients in the vector or matrix. So this is basically how media formats such as JPEG, MP3, or MPEG store our media files in a smaller size. Compressed sensing tagline is basically making do with less. So rather than sampling at a high rate and then compressing the sampled data, we would like to directly sense the data in a compressed form. So that is at a lower sampling rate. However, lower sampling rate means lower number of measurements, and this is classically not possible to solve because then you would have more unknowns than the number of equations. However, it turns out that we can solve this by looking for the sparse version of x, which is x naught. So to solve this relation, we can find the sparsest solution or the sparsest representation of solution. So this can be done by minimizing the L0 norm of x, because L0 norm is just the number of non-zero elements in the vector. However, this process of looking for the number of non-zero elements in a vector is an NP hard problem. So it is impractical for computations. However, the good news is that minimizing L1 norm estimates the minimization on L0 norm very closely. And to solve for a minimization of L1 norm, there are a lot of efficient algorithms that exist. And another interesting finding in this topic is that if X can be recovered by L1 minimization, then X is the unique solution to this AX equals B relation. Therefore, if X is non-negative and sparse, and in our research, we expect that the image consists of only non-zero elements, so the use of non-negative least squares will typically give the same solution. So instead of minimizing the L1 norm of X, we can actually minimize the L2 norm of this relation instead, with the constraint that X is equal to or equals to or greater than 0. And this can be achieved by using the LSQ non-neg function in MATLAB to perform the image reconstruction. It is also important to note that one of the requirements for this to work is that the matrix A must have randomness as its property. So in this research, the matrix A consists of random combination of elements 1 and 0. I'll explain in a minute how I physically represent these values in the actual setting. So I won't go into the details of the long design process, but this is the final design of the proposed system based on multiple iterative MCNP simulations, as well as taking into account other constraints such as the availability of equipment and hardware, as well as the cost of the materials used. These are some illustrations using the MCNP visual. Howdy, Assalamualaikum, and good morning, Malaysia. My name is Linda Anwar. I am a nuclear engineering PhD student at Texas A&M University. Today, I am going to talk about my PhD research, which is on the application of non-negative least squares to image gamma source for nuclear security. Let me start first with the motivation of this research. Close to 3,500 incidents have been reported in the span.
Assalamualaikum and very good afternoon. Welcome back to iNuSTEC 2020. So we are now at a session 3A, with the theme for this afternoon session, which is the environmental and safety. So my name is Ruguma Ramli. I will be the chairman for this afternoon sessions. Okay, a little bit brief for myself. Okay, I'm from University Tenaga Nasional. Okay, I'm a lecturer from mechanical engineering, and my research area is related to materials. Okay, so without further ado, I think we should start with our first presenter. Okay, I'm welcome Mr. Shamesh Raj. Okay, Pratasatri from Malaysian Nuclear Agency, with his research titles Environmental Radio Frequency Radiography, RFR, Safety Assessments at the Vicinity of Telecommunication Structure in Malaysia. Okay, Mr. Shamesh, the floor is yours.
All right. Thank you, Madam Chairperson. Okay. My name is Shamesh Raj Parthasarthi. I'm from the Radiation Health and Safety Division, Malaysian Nuclear Agency. So my topic will be on the environmental radio frequency radiation, RFR in short, safety assessment at the vicinity of telecommunication structures in Malaysia. Next slide, please. Okay. My presentation outline will cover the introduction, the objectives, the methodology of my research, results. I'll be focusing on the discussion, and finally the conclusion. Next slide, please. All right. Mobile phones, it plays an essential part of modern telecommunication, whereby in many countries, over half the population use mobile phones. The usage of mobile phones has been increasing exponentially over the past decades, in line with the needs of high-speed communication. So if you can see from my slides, as of first quarter 2020, Q1 2020, the number of mobile subscriptions in Malaysia was at 41.7 million. And then in conjunction with that, for the year 2020, the number of smartphones in Malaysia is estimated to reach 30.41 million. So in line with this, the telecommunication companies are generally establishing more telecommunication structures at every strategic location, as the demand for the mobile users are tremendously high at the stated areas, and also in order to ensure the quality of services to the customer. The communications in network service provider NSP and network facility providers NFP in residential area has raised concerns from the public about the possible radio waves effects caused by this structure. Therefore, if you can see, there are currently around 25,000 telecommunication structures in Malaysia. So this brings me to the objective of my research. Next slide, please. All right. The objective of my research paper is first to determine the level of radio frequency radiation present and to assess the potential exposure received by the general public at the vicinities of the structures. Secondly is to compare the RFR level based on the Malaysian Communication and Multimedia Commission, MCMC mandatory standard, and ICNIP, and also to ensure the radio frequency level, it complies with the reference level or the permissible exposure limit to the public. Next slide, please. Okay, the assessment location or my research, it focused on 25 telecommunication structures which were selected around several states in Malaysia, namely Wilayah Persekutuan Kuala Lumpur, WPKL, Selangor, Penang, Melaka, and Sarawak. Generally, these locations for this assessment were chosen based on public complaints. So when public complain at this particular location, what we do, Malaysian Nuclear Agency under the Radiation Health and Safety Division, we have conducted a safety assessment on all these particular locations. Please bear in mind that this assessment was performed at the accessibility of areas by the general public and places where public used to spend their times. Example, parks, bus stops, community halls, office buildings, schools, and so on. Next slide, please. Okay, the methodology of the radio frequency radiation safety assessment is basically developed by Malaysian Nuclear Agency with the recommended standard by ICNIP, International Commission on Non-Ionizing Radiation Protection, International Electrocommunication Commission, ITU, International Telecommunication Union, IEEE, Institute of Electrical and Electronics Engineering, and Canadian Safety Code 6. So the methodology can be divided into three main parts. First is to identify the RF source. So for this case, the RF source would be the antenna. And then next is to identify the points of measurement. As I mentioned just now, the location of the measurement was selected based on worst case situation, meaning that it's the nearest accessible location facing the antenna beam. So the antenna beam is a upward electrical radiation level. Therefore, we will be focusing all at the areas of the antenna beam and also at popular public places, as I mentioned just now, on the residential area, playground, and bus stops. So the safety procedures will be followed based on the recommendation by ICNIP, IEC, ITU, IEEE, and the Canadian Safety Code 6. So for each point, the measurements were taken for 6 minutes using the NADA broadband meter, which is a NBM 550. It's a broadband meter with the probe EF0691 with the frequency range from 100 kilohertz up to 6 gigahertz. So in this thing, I like to emphasize that the radio frequency level assessed is all above 2 gigahertz, right? And then the measurement was performed at 1.5 meter from the ground. The results were generally recorded in the power density in microwatts per cm square. Once the results has been recorded, it will be analyzed, and then furthermore, the results will be compared with the reference level or the permissible exposure limit as stated in the MCMC and the ICNIP guidelines. Next slide, please. Okay, this figure, it shows the RF sources and the equipment. Generally, whenever we did the safety assessment, we have to notify or we have to observe the RF radiation source, which at this case is the antenna. And then we have used two particular equipment. Firstly, on your left, the NADA NBM 550 broadband meter with the probe EF061. This equipment is capable of capturing the radio frequency radiation from the frequency of 100 kilohertz up to 6 gigahertz. This equipment, technically, it measures the overall broadband in terms of power density. Next, we have the selective radio meter, SRM 3006, with the antenna field model K0818, which is capable of spanning the frequencies from 27 megahertz up to 3 gigahertz. Example, when you compare these two equipments, the NADA NBM, it covers the whole frequency span, whereas for the NADA model SRM, we can select the particular frequency. Example, if a service provider M, it's operating at a particular frequency of 2.4 gigahertz, so we can set the particular frequency wavelength in this particular SRM, and then we can check what's the power density obtained or recorded at that particular frequency. All right. Okay, this shows the measurement procedure. So on your left, you can see, as an example, if there's a 15-meter mobile telecommunication base station or telecommunication structure, this structure, it emits the radio frequency, and then at this particular location, the results will be recorded on the NADA broadband meter and also the SRM meter. So if you can see on your left, it's the mobile telecommunication base station, or in short, it's a telecommunication structure. Example, it's transmitting at a power of less than 100 watts. And then on your right, there's a technical person he's logging the data in terms of the NADA broadband meter and also the selective radio meter, whereby these results will be recorded in the broadband meter and also the selective radio meter. The results are recorded in power density in terms of microwatts per cm square. And also, please note that this equipment is constructed, or it's fixed at 1.5 meter from the ground, as stipulated in the International Electrotechnical Commission. So next slide, please. Okay, this picture shows the points of measurement whereby the safety assessment has been conducted. If you can see at the middle, this is the telecommunication structure, or telco structure in short. So this radiation, it spans a very vast area, let's say around 100 to 200 meters from the particular telecommunication base station. Example would be at a residential area, at a community hall, at schools, office buildings, playground, parks, bus stops, and any other accessible location. So if you notice, the points of measurement indicated in the star is selected based on the worst case situation, generally facing the antenna beam, and also the popular public places, example residential area, playground, bus stops, and so on. So if you can see, the RF radiation from the telco structure, it spans the whole area of this, and then for each and every location we'll be focusing on the broadband safety assessment and also the selective radio safety assessment, and then each of every data will be logged and will be analyzed. Next slide, please. Okay, from here you can see the radio frequency reference level. As I mentioned just now, in the reference level by the ICNIP 2020 and also in the ICNIP 1998, we can see that they have three main things for the public exposure scenario. Example, for in terms of RF radiation for the public, we'll focus on the power density in terms of microwatts per cm square. So at a particular frequency from 2 gigahertz up to 300 gigahertz, the reference level or the permissible exposure level is computed at 1000 microwatt per cm square. So you can see that there's two exposure limit. One is for the public and also another one is for the occupational. So for this particular research, we have to focus on the radiation level from the public exposure point of view, which is at 1000 microwatts per cm square. Next slide, please. Okay, based on the results accumulated and logged, we have come out with the particular plot, whereby this plot, it refers to the radio frequency levels in terms of microwatts per unit area, microwatts per cm square, against the location of measurement, and also the comparison with the reference level or the permissible exposure limit. So if you can see, with all the 25 locations around the 5 states, location 1 to location 5 in Kuala Lumpur, location 1 until location 5 in Selangor, location 1 till location 5 in Penang, location 1 till location 5 in Melaka, and finally location 1 till location 5 in Sarawak. So you can see that the highest data logged was at 4.15 microwatts per cm square, which was recorded at location 4 in Selangor. And then the lowest was recorded at 0.50 microwatts cm square in a location at location 2 in Sarawak. So when you compare with this value 4.95 against the permissible exposure limit of 1000, so you will get the percentage of the exposure level compared to the permissible exposure limit. So please bear in mind that this results is based on the NADA broadband meter, which is the broadband meter which spans the frequency from 100 kilohertz up to 6 gigahertz. And for this particular research, all of the spectrum or the frequency detected was more than 2 gigahertz, and then therefore the reference level of 1000 microwatts per cm square were utilized. So next slide, please. So based on the results, the readings from the NADA NBM indicated the total radio frequency radiation present on site during the measurement. The range of the highest, it varied from 0.50 microwatts per cm square up to 4.15 microwatts per cm square. So this, when you compare this highest level of 4.15 microwatts per cm square to the permissible exposure limit, this level, it corresponds to around 0.42% of the ICNIP and MCMC exposure limit of power density for the public. So you can see from this, the result is 4.15 microwatts per cm square. You divide with 1000 microwatts per cm square and you times with 100%, you'll get around 0.42%. So this is the percentage of the exposure compared to the permissible exposure limit, which is very less than 1%. All right. So this result, it generally shows the broadband measurement from the NADA NPM 550. Next slide, please. So in terms of selective radiometer, we have also compiled all the data using the particular frequency emitted by the each and every of the antenna. So if you can see from this pie chart, you can see the 60% of the mobile signal are from the telecommunication structure, are from the mobile signal of interest. Generally, let's say in a particular transmitting telecommunication structure, there are three service providers: service provider M, service provider D, and service provider U. So you can check from each division of the frequency span which particular mobile frequency is transmitting at the highest power. So you can see of the overall 100%, only 60% is from the mobile signal of interest from the telecommunication structure. The next 22% is from other mobile phone signals, meaning that the radio frequency from the environmental radiation is not only from the signal from the telecommunication structure, it also can be from our mobile phones and also from other RF devices. And also, if you can see, 8% was contributed from the radio signal. Okay, when you see the radio signal is from the 86 megahertz up to 108 megahertz. And also 10% of the signal is from the TV signal, from the digital signal, and also from the satellite. So you can see that not 100% of the signals are from the telecommunication structure, which is contrary to the popular belief that when people see the telecommunication structure, they see that 100% of the signal is from the telecommunication structure. So this is untrue. Generally, around 60% or up to 70% of the signal is only from the telecommunication structure. The rest would be from the other mobile phone signals and also other radio frequency signals such as radio and television. Right, next slide, please. So as a conclusion, the radio frequency radiation measured in all the sites were well below the reference level and comply with the MCMC mandatory standard and also the International Commission on Non-Ionizing Radiation Protection standard for members of the public. So as I explained in the previous slide, the exposure limit is 1000 microwatts per cm square, but the highest level we obtained is only 4.15, so which is equivalent to only 0.42%, which is less than 1% than the permissible exposure limit. So based on these findings, it's believed that the presence of the radio frequency radiation emitted by the antennas from the telecommunication structure, it would not lead to any significant radiation exposure received by the public in that area. So you can see that at only 0.42%, the radiation level compared to the permissible exposure limit, which is at 0.42% and which is less than 1%, it's a very low. So it won't lead to any radiation exposure to the public around that area. In addition, the radio frequency radiation safety assessment, it should be done during the commissioning of new equipment or the antennas, and also during any modification of the equipment or the antennas. This is important because when the network facility providers or the network service providers, they install a new antenna, a new radio frequency safety assessment should be conducted in order to gauge the proper radiation level. So next slide, please. All right, so my final slide would be to share with you guys on the research and study on the radio frequency radiation health conducted by the World Health Organization. So World Health Organization, they have stated that a common concern about base station or telecommunication structure, it relates to the possible long-term health effects that the whole body exposure to the RF signal may have. But bear in mind that to date, the only health effect from the radio frequency fields identified in scientific reviews has been related to an increase in body temperature, which is more than 1 degree Celsius, from exposure at very high field intensity, which is only found in certain industrial facilities such as RF heaters. So these RF heaters is basically used in the industrial and also in the manufacturing side. All right. In terms of public, we have we don't encounter on RF heaters. All right. So the level of RF exposure from the base stations or the wireless network are so low that the temperature increases are insignificant, and overall it does not affect the human health. So generally, that's my study on the radio frequency radiation in terms of the environmental safety conducted on the 25 telecommunication strikes spanning 5 states in Malaysia. That's all. Thank you. And if you have any questions, please feel free to ask. Thank you and stay safe.
Okay, thank you so much, Mr. Shamesh, for your presentations. Okay, now we will continue with the second presentation from Malaysian Nuclear Agency, which is Mr. Faisal Izwan Abdul Rashid. Okay, with the research titles Radionuclide Analysis of the National Data Center Preparedness Exercise 2019, Malaysia National Data Center Findings. Okay, Mr. Faisal, the floor is yours now.
Thank you, Ms. Chairman. Assalamualaikum and a very good afternoon. My name is Faisal Izwan bin Abdul Rashid. I am the research officer attached at the Planning and International Relations Division, Malaysian Nuclear Agency. Presently, I am the manager for the CTBT National Data Center located in Nuka, Malaysia. So the title of my presentation today is Radionuclide Analysis of the National Data Center Preparedness Exercise 2019, Malaysian National Data Center MyNDC Findings. And for your information, this study was conducted together with my colleague, Mr. Mohammed Zulfakar Zulkafli. Next. Okay, here is my presentation outline for today. I have divided my presentation into 4 main sections, which are introduction, methods, results and discussion, and finally the conclusion. The points that you see below each section are basically the items that I will focus during my presentation. Nonetheless, if you need more explanation of the items, you can refer to my full paper once it was published. Okay, moving on to next slide. Okay, so I start my presentation by giving you this brief information. This study was conducted under the framework of the Comprehensive Nuclear Test Ban Treaty. The CTBT is basically an international multilateral treaty that bans all nuclear tests by anyone, anywhere, and for whatever purpose. It was adopted by the United Nations General Assembly on 10 September 1996, but unfortunately, it has not entered into force up until today. Malaysia is one of the contracting states to the CTBT. Malaysia has signed the treaty on 23 July 1998 and further ratified the treaty on 17 January 2008. And under the CTBT, Malaysia has established, among others, a national data center, in short we call it MyNDC, on 13 December 2005 at the Malaysian Nuclear Agency. The function of MyNDC is to provide technical information of CTBT-related events to Nuclear Malaysia as the CTBT national authority in the country. Next. As you can see from the slide, the picture is the MyNDC located in Nuclear Malaysia. To perform its function, MyNDC is equipped with appropriate hardware and software. that are used for monitoring and detecting nuclear weapon tests. In this connection, the team software that we always use for nuclear test monitoring is mainly developed by the Preparatory Commission of the Comprehensive Nuclear Test Ban Treaty Organization. In short, we call it CTBTO Preparatory Commission. At the same time, we also use the software from other developers for data analysis. Moreover, my NDC is also equipped with data and communication infrastructure, such as data servers, routers, UPS, as well as VSAT. This hardware is used for receiving, storing, and processing monitoring data for nuclear test monitoring. At my NDC, we also receive the monitoring data from the International Data Center located in Vienna, Austria. So we use this data for monitoring, detecting, and verifying nuclear tests. Next. Okay, in this slide generally, the National Data Center Preparedness Exercise NPE is a regular international exercise conducted among national data centers. It aims to measure the readiness of the national data centers to fulfill their duties in regards to the CTBT verification. In this exercise 2019, a fictional scenario possibly related to the violation of the treaty has been developed, and then the NDC is tasked to verify the nature of such scenario. The NPE 2019 was officially started on 22nd November 2019. Actually, we should present these findings from the study at the National Data Center workshop in Spain last April 2020, but the workshop was postponed due to the COVID-19 pandemics. In NPE 2019, a hypothetical scenario described that a trigger reactor accident had taken place on 30th July 2019 in fictitious location of Pavia Rhaetia, and a small release of radioactive isotope to the environment had occurred. The neighboring state named Istria, so in the real world, Istria is located in the territory of Austria, has provided its national radionuclide measurement. The data consists of synthetic particulate and noble gas radioxenon data measured at selected IMS facilities around the globe. The NDC are then tasked to analyze the provided data and to identify the potential source region of such release. Next. Okay, the provided data to the NDC consists of particulate data and noble gas data, primarily radioxenon isotopes detected at selective IMS radionuclide station. The particulate data comprise activity concentration of cesium-134, cesium-137, barium-140, lanthanum-140, as well as iodine-113, measured at 8 selected IMS stations at different date of detection. Meanwhile, noble gas data consists of activity concentration of radioxenon gases, particularly the xenon-131 metastable, xenon-133 metastable, xenon-133, and xenon-135. These radioxenon gases were detected at 2 stations, namely DEX-33 and VIP-00. Next. Okay, from the slide, you can see 2 figures. The left figures illustrate the location of the IMS station relative to the trigger reactor accident. From the figure, you can see the location of IMS station around the globe, as well as the location of the reactor itself. It is important to note that the station with the letter X has the capability to detect noble gas, while the letter P indicates that the station is capable to measure radioactive particulates. Moreover, to the right figure depict the chronology of the detection of particulate and radioxenon at IMS station. As you can see from the figure, the Pavia reactor accident occurred on 20 July 2019. The first detection of particulate measured at VIP-00 in Vienna, Austria. Then, the other station started to measure the particulate on 6 August onwards. For noble gas detection, 2 stations have detected such isotope, namely DEX-33 and VIP-00. This station detected the radioxenon gases on 2nd August 2019 up until 9 August 2019. Next. In this study, we have conducted 3 types of analysis, namely the particulate data analysis, noble gas data analysis, as well as the atmospheric transport modeling. In short, we call it ATM. In particulate data analysis, we have converted the activity concentration of particulates into relevant nuclide ratios such as cesium-134 over cesium-137 and lanthanum-140 over barium-140. The nuclide ratio will be used to characterize the source, whether it is coming from the severe sources or nuclear explosion. For noble gas data analysis, we use the same approach of particulate data analysis by converting the activity concentration into nuclide ratio, namely xenon-135 over xenon-133 and xenon-133 metastable over xenon-131 metastable. Then this ratio were further analyzed using the multiple and atmospheric xenon isotopic activity ratio as suggested by the literature from Martin Kalinowski 2010. The multiple atmospheric xenon isotopic activity ratio will enable us to discriminate the nature of the event, whether it is coming from the severe region or weapon region. Finally, we perform the ATM and we run the ATM in 2 modes, forward and backwards. For ATM simulation, we use the finding from particulate data and noble gas in terms of nuclide concentration. For backwards modes, we use software called WaveGrape, and for forward mode, we use high-split software developed by the USA National Oceanic and Atmospheric Administration. Next. Now we come to the result and discussion. This slide is the result of particulate data of cesium-134 and cesium-137, and we can see that the ratio of cesium-134 over cesium-137 for the 3 stations is almost constant and within 0.42 to 0.14, and therefore we can conclude that the material released are from the same source of material. Thus, it did not come from the multiple sources. Additionally, the ratio is above 0.01, which signifies that the source was highly probable from sources other than nuclear explosion. If in the case of nuclear explosion, we should expect to see the ratio below 0.01. Next. So the graph on the left indicates the ratio of lanthanum-140 and barium-140 over time for 3 stations. Again, the ratio is almost constant and smooth, and therefore it concluded that it comes from the same source of source material. Next. Okay, this slide shows the result of noble gas data analysis. The left figure shows the xenon-135 over xenon-133 and xenon-133 metastable over xenon-131 metastable activity ratio over time from 2 stations, VIP00 and DEX33. The findings show that the ratio are within 0.001 to 0.001, and we can clearly see that this ratio differs between stations. As the collection date advanced, the ratio also increased, and this ratio was further analyzed using multiple atmospheric xenon isotopic activity ratio that we should be covered in the next slide. Okay, in this slide, we can see the figure on the left is the multiple atmospheric xenon isotopic activity ratio diagram developed by Martin Kalinowski 2010. The diagram has 2 regions, severe region and weapon region. And the severe region on the left indicates that the source might be coming from the nuclear power plant as well as the radioisotope production facilities, and the weapon region indicates that the source might be coming from the nuclear test explosion. And we have plotted the radioxenon nuclear ratio into this diagram, and we found out that all the ratio fall within the severe region, and therefore we can conclude that the source of the isotope might be coming from the severe region rather than the weapon region. Next. Okay, once we know the characteristic of the source, we want to know where the possible source region for such measurement. To do that, we conduct ATM in 2 modes. This slide indicates the result of ATM for the backward modes. The backward modes ATM is conducted by simulating the progression of radioactive plume from the IMS station to backtrack to the date of interest. In this case, the date of interest is 30 July 2019. Before I start explaining the result, it is important to note that within the region, there are two main isotope production facility in the region, namely TICO and IRE, highlighted in orange and light blue. We have performed the ATM for all stations except that for NEP48 due to the unavailable SRS data. This figure on the left represents the backward ATM for 4 stations. The results show that the PSR for nuclide detected for CNP21, VIP00, KWP40, and LYP41 may include the Pavia reactor, nuclear power plants, as well as the TICO and IRE IPF. Next. Can we go to next slide? Okay. The figure depicts the result of the backward ATM for IRP36, REP55, and DEX33. The results show that the PSR for nuclide detected at this IRP36 and REP55 may include Pavia reactor, nuclear power plant, and TICO and IRE. But no, the previous slide, please. Can we go to the previous slide? Can we go to the previous slide? Next. Yeah, this slide. Interestingly, from the backward ATM, we can confirm that the DEP33 station will not be affected by any release from the Pavia reactor. As you can see from the plume, it did not intersect with DEP33 station at all. Can we go to next slide? Okay, so this slide simulate the forward ATM from the Pavia reactor site. The release time is 30 July 2019 in the morning. We used 200,000 particle release for a duration of 24 hours. And from the animation, you can see that the dispersion of radioactive plume from the reactor site on 30 July 2019 to the surrounding region and the IMS. From the simulation, you can see that the plume did not intersect with DEP33 station at all. So this result is in line with the result from the backward ATM that I mentioned previously. Next. In this slide, we can see the pattern of xenon-133 measured at the VIP00 station as well as the simulated concentration. The evidence shows that the nuclide might be coming from the Pavia reactor due to the identical pattern, even though the concentration is differ very much. But in this study, we just perform a simplified modeling, and we did not take into into consideration the other atmospheric parameters such as scavenging, precipitation, humidity, and many more. And therefore, if we can do that, we could achieve a result close to the actual measurement. Of the simulation is only to highlight and to focus on the pattern of detection. The pattern is identical. Next. This slide simulates the forward ATM from TICO isotope production facility located in Netherlands. The result time is 30 July 2019. We use basically the same release parameter as the release from Pavia reactor. And from the simulation, you can see that the plume did not overlap at all with 2 stations, RUP55 and CNP21 located further east. This shows that the release from TICO will not have any impact in terms of measurement to both stations. Next. This slide is a summarized result from the forward ATM, and we can see that the release from Pavia will affect all stations except depth 33, as I mentioned previously. Meanwhile, release from the TICO will affect all stations except two stations, CMP21 and RUP55, and lastly, release from IRE will affect all stations. Despite this IMS station detected those nuclei, it is important to note that 4 of these IMS stations are not certified IMS station, namely VIP00, RUP55, IRP36, and LYP41. And therefore, we should take cautionary measure because the calibration parameters at this non-certified IMS might be questionable. Next. The figures show the dispersion of radioxenon gases from the operation of medical facilities and nuclear power plant around the globe. We can see that the Pavia reactor accident is collocated in the region with dense population of nuclear power plant, as well as the 2 global main medical isotope production facilities, IRE and TICO. And therefore, we can classify the region of the study is a complex environment for analysis. It is because during the normal operation, the nuclear power plant and medical radioisotope production facility will emit certain amount of radioisonon gases to the environment, and this could have a major impact on the IMS station. Next. So from the analysis, the findings draw from the following conclusion. The abnormal measurement of nuclei at DEP33 station were unlikely from Pavia reactor. The particulates and radioxenon detected at VIP00 were most likely from Pavia reactor site. Detection at the other station could be originated from Pavia reactor site. However, owing to the complex environment in the region, the nuclear emission from IRE and IPF as well as nuclear power plant could not be totally ruled out. And with that, I end my presentation.
Okay, thank you, Mr. Faisal, for your presentation just now. So then we'll continue with our third presenter, okay, Nur Fadilah Ismail from University Technology Malaysia with the research title Human Health Risk of Radon 222 and 220 radon exposure from Geological Features in Negeri Sembilan, Malaysia. Okay, Puan Nur Fadilah, the floor is yours. Miss Fatman.
Okay. Assalamualaikum warahmatullahi wabarakatuh and very good afternoon to Madam Chairman. My name is Nur Fadilah binti Ismail from University Technology Malaysia and also from Malaysia Nuclear Agency. So today I will share with you about my project. So my project is about human health risk of radon and thoron exposure from geological features in Negeri Sembilan, Malaysia. So this project actually I conducted on years 2019 last year, and until now it's still continues for others part of my research. So next. Hello, next. Okay, in my presentation outline, I try to divide with 5 parts, which is starting with introduction, and then it's subjective, following by methodology, then result and discussion, and last is about conclusion. Next. Okay, in my introduction, actually I think everyone know that radon and thoron is radioactive gases, so it's very dangerous actually in our life, and they have the properties, physical properties such as tasteless, odorless, and also colorless, which is we cannot see in our own eyes. And both of radon and thoron have very short half-life. For radon, it's 3.8 days, while for thoron, the half-life is 46 seconds. And for your information, that radon and thoron come from decay series of uranium and thorium respectively. And for information that radon and thoron are ubiquitous in our nature, it comes from rocks, and also distribute or disperse to soil, water, and go to atmospheres. And for your information, radon is very dangerous because it's considered as the second leading cause of lung cancer after smoking. Next. Okay, I have 3 objectives in my research. First is to determine the concentrations of radon and thoron in the environmental sample, and the second one is to determine the concentrations of radon and thoron with geological features aspect. And for objective number 3 is to estimate the exposure dose of radon and thoron with their corresponding to human health hazards. And next is about the methodology, how I conduct my research. Next. Okay, in my methodology, I try to divide in 5 parts. First part is about sampling location. In this part, I determine only 44 sampling point in Negeri Sembilan, which is then I try to get the coordinate for each sampling point using the GPS equipment. And the second one is, and the next is to determine the geological formation for each sampling point. So this part, I try to determine using the geological map, which is get from the geological department in Malaysia. Okay, and then the measurement technique. In this technique, I prefer to use STRAT7 detector, and then I will measure 3 types of sample, which is sample of water, soil, and also air. And then for the analysis part, I will analysis further about radon and thoron concentration in all the kind of the samples, And then after I get the concentration result, I try to calculate or get the annual effective dose from each type of sample. So then I also analysis using the RDS map, and the last one is try to get the correlation between all of the aspects. And last is discussion, which is I will show you the results and others. Next. So here, this is the peninsular maps of Malaysia. So as you can see that the central one is Negeri Sembilan. So in Negeri Sembilan, it actually consists of 7 districts, and the coordinate is lying at the point 2 degrees with 45 minutes in north, with 102 degrees and 15 minutes in earth. So the total land areas in Negeri Sembilan is 6,686 kilometers square feet. So from at these areas, I collect around 47 locations. As I tell you before that I use GPS to get the accurate coordinate. Okay, next. So this is the distribution of my sampling point. As you can see that it's scattered in Negeri Sembilan area because I choose or I prefer to do these techniques because of I refer to the geological features, and then when I agree with that location, and then I make it as my sampling point. So total of location is 47. Nice. Okay, as you can see in your screen, so this is the geological maps which is I get from the geological department Malaysia. So as you for your information that in Negeri Sembilan it consists of 6 types of geological features, which is acid intrusive, Carboniferous Permian, Quaternary, Ordovician Silurian, Permian, and also Triassic. All of this kind of geological features has have different kind of their structures of soil and also rocks. Okay, next is about the measurement flow chart. Okay, this is how I conduct my measurement. Okay, as I tell you that I use RAD7 detector in my measurement, so I conduct in 3 sample of environmental, which is in soil, in air, and also in water. So for soil, I apply probe to insert the probe in the soil at the depth of 80 centimeters from the surface, and the counting time is about 30 minutes. And for the RAD7, I put it in a mode, sleep mode. So same with air, the measurement will conduct in 30 minutes with sleep mode, and for air measurement, I will not use any probe. The third is about how to conduct the measurement in water. So in water, I apply the RAD7 water accessories. For the RAD7 mode, I put it in a watts 250 mode. And same with others, the counting time is only 30 minutes. And after I get the radon and thorium concentration, I will proceed with the analysis to get the radiological potential hazard. So the next slide is about the pictures of my measurement. So in the pictures 4, it is shown to you that the measurement setup for soil. Okay, so this is the probe, and in the bottle, the blue bottle is actually the desiccant. So the function of desiccant is to absorb the humidity and then to maintain the humidity of the RAD7 must be lower than 10%. So this is to make sure that the RAD7 is working in a good performance. And the figure 5 is the measurement setup for air. following by the figure 6. So this is the water water measurement. So in this part, in the water measurement, I only measure the radon concentration in water only. No thoron in water. Okay, next. Okay, this is a part of analysis of data. So after finish the measurement, I will transfer all the data in the capture software by connecting the software by connecting the Red7 equipment to my computer, and the pictures of figure 9 shows the data acquisitions and also all the details of my measurement, including humidity, temperature, the radon and thoron concentrations, and all. So after that, we will proceed with the radiological potential hazard. So in this part, we will calculate the annual effective dose in millisievert per year. So this part, I will 100% refer to the ANSEER 2000 report. So in this part, in this effective dose part, to get the dose in air, so we just follow this equation, and also with the water, which is we can get the radon from the inhalation and ingestion. So this is also the equation which is I get from the ANSEER report 2000. So you can see here. Okay, so now I go to the discussion part. Okay, in my discussion, in this study, the concentrations of radon and thoron was recorded in unit becquerel meter cube. And the result from my study is presented in the graph below. Okay, as you can see that the concentration of air is in the range of 5.67 to 193 becquerel cube, with the average of 56.5 for the radon concentration. While for the concentration of thoron, the range is around 10 to 100 to 156.67, with the average 26.67. While for soil, the concentrations of radon is around 6.67 to 12,595, with the average of 345 becquerels per cube. And then the concentrations of thoron in soil, the average is starting from 11.67 to 10,316, with the average 331.95. And result for water, the average is starting from 316.67 to 186,500 becquerel cube, with the average of radon 20,000 becquerel cube. While no any thoron detected for water. And as you can see that the concentrations of thoron of radon is more higher compared to thoron in all types of sample. This is because of the content of uranium and thorium in the certain cases, which is because of the uranium is higher compared to thorium. So as we can see that radon, we cannot neglect it because it also have potential health risk to us. Okay, next. Okay, the result in air show that the concentrations of radon and thoron were considered high because the average of radon is not in the range suggested by WHO, which is within limits 10 to 15 meter cube. So this is wrong. And while for soil, the concentrations of radon and thoron in soil were also considered high because it exceeded the range suggested by ANSIA, which is up to 100 to 300 becquerel cube. For water, the concentrations of radon were considered low when compared to the WHO safe limit for drinking water, which is the limit for WHO is about 100,000 becquerel per meter cube. Next. So in my study, I also conduct or compare the concentrations of radon and thoron in soil with their geological aspect. So as you can see that the highest radon and thoron were you can see the highest radon and thoron in acid inclusive rock compared to the others. So the study revealed that the concentrations of radon in granitic region is considerable higher compared to other silicious features due to high concentrations of uranium and also thorium. Okay, the next is about next slide. Okay, I also conduct the concentrations of radon in the various types of each waters. So here is the types of water, which is I do to compare the concentrations of radon in tap water, hot spring, seawater, lake, and also waterfall. So as you can see that the highest is in hot spring with 186,000 with 500 becquerels per meter cube. Okay, compared to the others, you can see in this histogram graph, only hot spring is exceeded the limit, the set limit by WHO compared to the other kind of water. So, if the water consists of high concentrations of radon, so we need to treat the water in order to reduce the radon in the water. That is the advice by the WHO. The next. Okay, this is the radiological potential hazard due to the assessment of exposure dose of radon through the inhalation and also ingestion is summarized in table below. So as you can see that the dose come from air is around 0.54 for radon and 1.88 for thoron, while for water from ingestions, so 0.04. So the recommendation and safe limit for radon dose intake is for air is about 3 to 10 millisievert by ICRP, while for WHO is 10 millisievert per year. So the dose recommendation by WHO is about 0.1 millisievert per year. Okay, now it's about the conclusion. Okay, 4 conclusion that I can conclude in my study. The first is about the concentration of radon and thoron in soil, air and water are various from places to places, and it may be influenced by the geological background of the location. And the second is about the assessment of radiological potential is important to ensure that the annual effective dose received by public is safe and below the recommendation limit by WHO and also ICRP. So the third conclusion is the exposure due to the high and to the exposure due to the inhalation and ingestion of high level of radon and boron will give you the risk of human health, such as lung cancer and also stomach cancer. So the number 4, result obtained is very important as a baseline data and will be very useful to public as knowledge for future reference. And that's all from my presentation. Thank you.
Okay, so thank you so much, Puan Nur Fadila, for your presentations. Okay, now I would like to call upon Puan Aini Amira binti Jasni, okay, to present the research for two-dimensional array of NPPC and CSI for radiation monitoring for the types. Okay, Ms. Aini, the floor is yours now.
Assalamualaikum warahmatullahi wabarakatuh and a very good evening to everyone. My name is Aini Amira binti Jasni. I am master student from Music Technology Malaysia. I would like to share a part of my research work in my master. And my supervisor is Prezat Ibn and my co-supervisor is Dr. Izzah Hasmani binti Hashim and Dr. Izzati binti Ahmad. So title for sharing today is two-dimensional array of NPPC and system arrayed for radiation monitoring for the batch. Next please. Here is my outline for sharing today. I will begin with introduction for my work. Next is my objective, my methodology, my result and conclusion for this study. Next. First of all, the radiation monitoring is used widely in various applications, such as application in medical procedure, homeland security and safety, airport security, and environment monitoring.
Ada kereta.
And industrial application. It involves exposing a test object to radiation so that the radiation penetrates the objective and the defect position that can be resolved. This is very important as preventive measure before an accident occurs and as well as to respond to the radiation incident. So nowadays, the current existing system for detecting radiation using sensor is multiple PMT, and second is advanced photodiode APD. Next. Okay. PMT is a photon detection device that use the photoelectric effect combined with the secondary emission to convert the light into the electrical signal. PMT is a photon detector consisting of the translator, photocutter, and electron multiple anode. But it has a disadvantage, which is it needs a stable high voltage, and PMT cannot be used with a small magnet, and it's fragile, costly, and large in size. And the response time is fast. The APD is a self function as a photocutter in the PMT, and it is a highly sensitive semiconductor photodiode that exploiting the photoelectric to convert the light into the electrical signal. And APD have a high detection efficiency than PMP. But he has a weakness, which is it unable to measure low energy, and the size of APT is small, and the response time is slow. Therefore, the radiation monitoring should be able to detect radiation efficiency in a short time at high and low intensity, and can provide some information. And efficiency radiation and position monitoring system is required and useful for preliminary security insertion and radiation efficiency detectness of the response. Next, in this study, PMP and APD are replaced with a new device with excellent photon content capable, known as multi-pixel photon counter MPPC. Okay, next. Here is my objective. First is to design and construct two prototypes of MPPC array module. Second, to determine the detection sensitivity for beta and gamma radiation for both prototypes. However, they have a limitation for my study, which is one, to the array position sensitive detection rate is a small size, with transmission 2 times 2.4 cm, and second prototype is 2.5 cm times 4.5 cm, and the prototype be tested in static condition only. Next. What is MPPC? Okay, MPPC is a is a new type of silicon multiplier device. It is a new type of photon counting device made of material turbulent photodiode pixels operated in GPU. MPPC have a size, and MPPC is insensitive to magnetic. MPPC have a high gain, which is 7.5 times 10 of and which is just on volt the bias voltage. And the MPPC operating voltage. Next. Okay. In order to get a high performance photon counting and a large maximum translation light transmission, the MPPC detector need to coupling with the translation material. So most of the current application nowadays, they use inorganic material because of the inorganic translator has a high light output and very common use in nowadays. So hence, and in this study, we focus on inorganic translator. So we choose system iodide because it is a slightly hygroscopy compared to another translator, and it can handle without any protection. System iodide crystal has much longer translation decay time than NiTl and BGO. Even NiTl has a better light transmission properties compared to system iodide, but it is so hygroscopy and easily tempered. And the damage on the NaTl, we can see where the Ni turn into the yellow, so it's not suitable for humidity in Malaysia. So TL was chosen as a translation crystal to provide excellent photon in order to get maximum performance. Next slide, please. Readout system used in this. E0 is stand for extended analog SIPM integrated readout chip. E0 is optical measurement for SIPM, and it able to measure photon counting. And E0 have 64 channel and 16 channel, so it comfortable for my research. E0 have low crosstalk, and it also have the electronic noise is low, so we can set the threshold that we want. And the power supply for the E0 is low, less than 5 milliwatt per channel. Next, please. Here is my methodology for my research. My methodology divided into three part, which is first part is design the prototype housing of NDPC and system iodide crystal, and the second part is channel testing. The third part is position sensitivity experiment. So my first part is I design the prototype. So we can see the above picture is a housing first prototype, and the below is a housing prototype 2, and the dimension for my prototype. So each NTPC will couple to the system iodide translator, and the surface of system iodide translator will polish using sandpaper to make sure the surface of the translator will smooth and clear, and the system iodide was cleaned by using the alcohol to propanol, and to couple between system iodide translator and the MPPC was used by using the silicon oil. Silicon oil is used to allow the propagation of photon signal from translator to the MPPC. The reactive index of the silicon oil and MPPC is nearly same. So it can allow the photon signal from translator to the MPPC. That's why we choose the silicon oil and MPPC. Okay, next please. For my second part is the signal testing. So here is my experiment setup for testing MPPC performance. So the prototype was placed in a black box because we want to get the black environment, and the photon electron threshold was set from 0.5 PE, and all the for all the MPPC in array will be tested by using radiation source, which is cobalt 60 and tritium 204, and the prototype is placed in a black box, as I mentioned before this. And this system, the optimum delay to get the signal, the good signal, is 15 nanoseconds, and the operating voltage for the MPPC is adjustable within the range. We set the operating channel for the MPPC is around 58 until 65 volt. And the raw data, and then next, the raw data will be analyzed by using root software in order to resolve the number of outlet, and we will plot into the ADC distribution histogram of the pin profile. Next, please. Okay. For the third part, in this experiment, they have two position condition be tested. We can this second part is below x 2y 3. Okay. The radiation source in middle and the purple. So after we analyze by the root, the peak position was determined by the Gaussian distribution. So the signal spectrum for the histogram optic can be analyzed by calculating area underground. So here is a formula for the Gaussian function. So Gaussian function will in random statistical of nuclear measurement. So from the Gaussian, we will fit in the function. We will normalize the condition equal to 1. So the Gaussian function will fit, so we can find the full energy peak for this for the signal. So full energy peak is the amplitude Gaussian function in a Hawthorne distribution for each peak. So by using this full energy peak event formula, the performance of the prototype is analyzed by the 2D plane monitoring, 2D plane profile monitoring. Next, please. So once the histogram and PET calculated and plot, so we can perform the number of the part into the image. So we will use this formula. We will use the light intensity as a function of the length we described by this formula. Because the information could be used from the source, because it's directly since each MPPC was connected to a single system iodide. So the scattered image with intensity can be plotted for the prototype 1. Next. So for prototype 2, same process is required to exert the information to form the image. In this example, for the prototype 2, the sensation photon will move within to the right or to the left side in the sensation sensilator. So the number of the photon N1 and N2 on the right and the left and the PC located at the effective end of the sensilator with this formula. And after we taking root of the product number of photon signal N1 and 2, we get we can N2 times N1 this formula. So we can calculate the total number of photon signal at MPPC1 and MPPC2. Okay. Next. Okay. Here is my result. So after we analyze the result by using explanation equation, so we plot into the plane monitoring to plane profile, and we can see that the full result show that the beta is higher than the gamma for all position, even we change the position of the radiation source. So the highest count at all positions is shown where the radiation source is placed. And we also calculate the efficiency of the prototype. This efficiency is a measurement of the presence of radiation that detect or boron yield that emitted from the source to the NPPC. So the efficiency for the prototype 1 with the beta is 8.86%, and with the gamma is 18.51%. So next slide please. Before this, next. Before this, before. Next. Next. Okay, back. Okay, so for the overall, the both outside array are visible in show the radiation position for both stars, and the 2D plane monitoring equipped in differentiate high and low radiation count, and the intensity of the beta are higher compared to the gamma, because the energy deposited of the beta is higher than the gamma. Beta radiation emitting a fast moving of the electron or the positron, where the gamma radiation emission of the gamma radiation emit a photon. So the beta radiation have high ionizing compared to the gamma. So prototype 1 has a better than prototype 2. Due to the prototype 1 already detected the sensation photon distribution. Prototype 2 cannot detect 2 bits on the same line simultaneous, and the absolute efficiency of the prototype is first. Prototype 1 is more efficiency than prototype 2. Next. To the conclusion, prototype array of 8 MPPC and with 8 system iodide translator has been developed and evaluated the performance of the position sensitivity prototype based on the translated array. The position sensitivity response to the radioactive source, gamma and the beta, was explained in terms of photon distribution for each condition. It shows a good agreement between the sun position and detect position contributed to the good position monitoring. So, for vision, and this system could be used if we improve the size of the detector and the range of the detection. Okay, that's all from me. Next. Thank you.
Okay, thank you, Ms. Aimee Amira binti Jasni for your presentation just now. Okay, so then we will continue with our second keynote speaker for today, which is Prof. Nicole Kajang from Helmholtz-Zentrum Berlin, Germany, with the titles of neutron imaging. Okay, Prof. Kajang, the floor is yours now. Thank you.
Okay. Thank you very much. Good morning from Berlin, Germany. Thank you very much for giving me the chance to present this talk on your meeting. And I'll be very glad to show you some results of neutron imaging based on our experience over about 15 years of having a neutron imaging experiment or instrument at the research reactor here in Berlin. So next slide, please. So here you see very nice, the very nice location of the Helmholtz-Zentrum Berlin. We are located at the southwest part of Berlin, close to the touristic area Wannsee. So you see here a picture from the top, and you can recognize very well the campus of the institute. So we have two campus area in Berlin, the one Wannsee, what you see on the picture. Next, please. So here at this campus, we have the research reactor BR2. And next, please. So at about 20 kilometers away, we have the next campus area where the synchrotron ring BESI-2 is located. So unfortunately, this year the reactor was shut down, and we don't have any more the capability of performing of investigations with neutrons. Next, please. So I'm belonging to the Institute of Applied Materials, where imaging is very important experimental method. We have imaging with neutrons, with X-rays and synchrotron radiation. So for this, we have different experimental facilities. One is the neutron tomography facility at the research reactor, which is no more existing from this year, but I'll show you our experience and results from this facility. We have one micro CT lab with X-ray tomography scanner, where we can perform tomography with conventional X-rays. And we have access to the synchrotron tomography beamline at the synchrotron ring BESI. In addition to this, we have 3D analytics lab, where we can process and analyze the data from the tomography experiments. Next, please. So when we start with imaging, we should understand how it's working. So for this, we need some radiation in order to penetrate the sample and give us a picture about the inner structure of this system. So here you see the radiation is penetrating the sample and giving us a picture about its internal structure. Sometimes, or in general, this type of radiation is harmful for the human body. Therefore, the observation should be performed with some detector, as shown here. So usually we are using some kind of digital detector, and then we can save the information on a PC or some computational system. This gives us the chance to perform data processing and analysis after the experiment, and also to observe some dynamic experiments. So next, please. So sometimes we get image like this, and this means that something wrong went in the experiment because we don't see anything. I think you are not seeing as well. The structure of the sample. The reason for this failure is that we didn't took account for two main parameters of the imaging experiment. So the first one is, next please. So the first one is, the first parameter is contrast. So we should have contrast in order to see the features. And next one, please. Also, so these are two main parameters which we should take into account when we are going for performing of imaging experiment. The resolution depends on the beam collimation or optimization and on the detector development. The contrast which we observe in our images depends on the interaction of the radiation with the matter. In this case, neutron interaction with the matter, which can be absorption, scattering, or even magnetic interaction because the neutrons have a magnetic moment. Next, please. As we saw, actually, the main components of the imaging experiments are source, beam collimator, and detector. When we put the sample in the beam, then we get a transmission picture on the detector, and the transmission is proportional to an exponential function where the attenuation coefficient and the thickness of the sample are parameters. So you see on the detector that we have different contrast or different transmission. And because this sample has the same thickness over its volume, this means that the beam or the transmission depends only on the different attenuation coefficients. So the attenuation coefficient is property of the material, and the different materials have different attenuation coefficients. So next, please. This type of geometry was implemented in our neutron imaging experiment. So you see the beam is transported through a neutron guide, and at the end of the neutron guide we have a pinhole which actually defines this point source geometry which we saw before. So at certain distance after the pinhole we have the sample and the detector, and this distance we need for a beam collimation. Next, please. So here you can see again our neutron imaging experiment, which was installed at the reactor. So due to the curvature of the neutron guide is transporting the neutrons and it can be curved. In this way, only low energetic neutrons can be transported. So this means that only the low energetic neutrons will be reflected from the walls of the neutron guide. Therefore, the spectrum of the neutron beam is only called neutrons or low energetic neutrons, as you see on the top of the diagram. At the end of the guide, we have relatively high neutron flux of about 2.7 10 to the 9 neutrons per square centimeter and second. The beam at the detector is about 20 by 20 centimeter. We have different instrumentation at the instrument or at the experiment where we can use polarized neutrons, monochromatic neutrons, or even perform grating interferometry. And we have two labs, complementary labs for performing imaging with X-rays and also, as I mentioned, analyzing and processing of our experimental data. So next, please. So here I'll go step by step and show you how we can improve the resolution and how we can use different contrasts for neutron imaging related to absorption, scattering, or magnetic interaction. So in case of detector development, next please, we can optimize the setup for detecting neutrons. In case of neutron imaging, we are using actually digital detector based on CCD camera or CMOS camera, as you see here. So with the lens of this camera, we can focus on the scintillating screen, which converts the neutrons to visible light. We have a mirror in order to prevent that the digital detector is placed in the beam, because the electronics will be damaged. So this is the setup for neutron imaging, detector for neutron imaging. So here we can optimize the scintillating screen and or the optical system of our detector in order to improve the resolution. You can see on the right that with standard setup several years ago, we could get a resolution of about 200 to 300 micrometer. So this is what you see here is a test pattern where actually the stripes which can be resolved is giving us the achieved resolution. Next, please. In case of optimization of the neutron screens or the scintillating screens, we need different converter materials because the neutrons are neutral, so they don't have a charge. This means that they cannot they cannot produce scintillating in scintillating materials because they don't have a charge. So therefore, we need a converter materials who or which can absorb the neutron and produce some charged particles, like 6 lithium or lithium-6, which absorbs the neutrons and produce alpha particles. Or next, please, or gadolinium, which produce converse electrons, which can be used also for the scintillating process. So the two types of converting materials can be used. The difference between them is that gadolinium has much higher probability for absorption or much higher cross-section for thermal neutrons, which means that with gadolinium-based scintillators, we can use very thin scintillators and increase the resolution. The problem is that the gadolinium-based scintillators have very low light output, which means very long exposure times. So next, please. In order to improve the optics, we can use lens systems which are dedicated for digital photography. Actually, we have quite good lenses which are commercial available, and here are two examples of this, where we can achieve, with the first one, we can achieve about 30 micrometer pixel size, and the second one with focal length of 200 millimeters, we can even achieve one-to-one imaging, or here the pixel size is limited by the pixel size of the detector, and here it is 13.5 micrometer. So next, please. So here you can see the effect of the optimization of the detector system. For the first image, we have scintillator of 200 micrometer, 6 lithium fluoride scintillator, pixel size of 100 micrometer and exposure time of 20 seconds. If we improve the optical system and get a pixel size of 30 micrometer, you see that we have considerably improved resolution. And at the end, we can improve our scintillator using very thin gadolinium sulfide oxide scintillator based on gadolinium. So you can see the thickness is only 5 micrometer. The pixel size is the same, 30 micrometer, but the exposure time increased 6 times. So it's 126 seconds. but the resolution can be improved down to 60 micrometer. Next, please. So this means with improvement of lens and scintillator, we can improve the resolution. We can go even further and use this kind of infinity corrected optics where two lens systems are facing each other. In this case, we can use optical magnification. So we are no more limited by the pixel size of the detector. And you can see here the ratio of the magnification depends on the focal length of the two lenses. So if the ratio of this focal length is 2 times, this means that the pixel size is the half of the pixel size of the detector. So in this case, we can go to 6, 3, or even 1 micrometer, choosing the right lenses. Of course, the field of view goes down. So you see from 30 millimeters, it goes down to 7 millimeters. But finally, we have so nice and high resolution that actually we can investigate very small samples. Next, please. So you see here the result of this high resolution setup, that with this optical magnification we can go down even to resolution of about below 10 micrometer with a pixel size of 3.4 micrometer. This resolution is really very impressive, and you can perform very nice neutron experiments, neutron imaging experiments, and resolve very fine features. Of course, the exposure times are quite long, but the most impressive thing, which is actually very important, next please, is that for example, high flux neutron sources, you can perform dual mode imaging, crossing neutron beam and X-ray beam. In this case, you have similar resolution because the X-ray images usually have resolution down to below 10 micrometer. And by using of this high resolution neutron detector system, it is possible to perform imaging with the same resolution. If you have enough neutrons, even the time resolution will be the same. So in this case, you can perform complementary measurements simultaneously. Next, please. So here, there is an example where we see investigation of reservoir rocks or rocks with oil in there. This is very important for the oil industry in order to find petrol in the rocks. And on the left is the neutron tomography, on the right the X-ray tomography of the same rock. And you see that the neutrons see more the hydrogenous area, or the area where we have some probably oil or organic stuff. And the X-ray is giving you the morphology of the rock, where you can see some metal inclusions or different minerals. So the complementary investigation of simultaneous imaging using X-rays and neutrons is giving you much complex information about the sample. Next, please. Increasing the resolution, we can also investigate very complex systems like batteries. So here you see one type of titanium battery with liquid electrolyte, and here we performed very high resolution neutron tomography with time of about 7 minutes. So you see the pixel size was 8 micrometer, and the time step between two tomographies is about 7.5 minutes. In this way, you can see how the lithium electrode or how the lithium anode is diffusing in the carbon-based electrode or cathode. So in case of discharge, we have penetration of lithium ions in the cathode, and the tomography is giving us the chance to estimate and also to see in 3D what is the lithium consumption in the battery with the time. We can see some defects, and we can see also some expansion of the electrodes in the battery. So this means if we combine the time and spatial resolution in a good way, then the neutron tomography help us to see very good the distribution of the lithium in such kind of batteries, because the neutrons interact with the lithium very strong, and the absorption is very strong actually for neutrons. So next, please. So, but for some dynamic processes, 7 minutes is too long, as shown in the previous experiment. So if we want to investigate, for example, water uptake in plants, or processes in fuel cell systems, or hydrogen storage materials where the neutrons are also very beneficial because of the strong interaction with the hydrogen, then we need much higher speed for the tomography, or in order to see the system in 3D. So next, please. Therefore, we performed one experiment in order to test how fast we can measure in 3D with neutrons. And here we investigated plants where we used the contrast agent, heavy water. We just removed the water from the soil and put heavy water in order to see the speed of the water uptake through the root system. Next, please. Then we went to the most powerful reactor in the world. This is the reactor ALL in Grenoble, France. And then we succeeded to perform tomography in 1.5 seconds. This means that we see the state in the system in 3D with a timestamp or time step of 1.5 seconds. Next, please. Just start the video. So here you can see actually how the waterfront in the root system is going through the soil, and this is showing us actually how the root is reacting to the contrast agent in 3D. So you can select every root from here and see its activity. So next, please. Due to the fact that heavy water is absorbing or attenuating the neutrons not so high as the normal water, and then after injecting the contrast agent, the roots which uptake heavy water starts to disappear in our tomography because they lose contrast. So this means that we can calculate actually the the speed of water uptake for each root and give a map of activity of the root system of the plant. This is very important for investigation, for example, how the roots of the plant is reacting on some contamination of the soil, or some draw stress of the root or dehydration, how the root is reacting to some extreme conditions. So next, please. So up to now we saw applications or contrast which is related to absorption, contrast, where we use a polychromatic beam. So we use all the neutrons from the research reactor. But in order to get a contrast, for example, of diffraction in our sample in polycrystalline materials, then we can use monochromatic neutrons. And this is one example of using neutrons with wavelength of 4 angstroms. And the sample was a welt of 2 steel plates. So you can see the weld and you see some diffraction contrast from the weld. Next, please. In order to prepare monochromatic beams, we use double crystal monochromator as shown here. From the polychromatic beam, we can pick only one certain wavelength. And we can change the wavelength continuously from 2 to 6.5 angstrom. And these wavelengths actually are very suited for diffraction experiments, as you know. Next, please. This helped us to distinguish between martensitic and austenitic phase in some metastable trip steel under mechanical loading. So you see here that for one certain wavelength of 4.2 angstroms, we have two different attenuation coefficients for austenitic and martensitic state based on diffraction. So they are attenuating the beam in a different way. And this gives us the chance to distinguish between two different phases in the 3D volume of the steel samples. So you see on the right picture, the left part is just torsion of the steel sample. On the right, you see the tensile experiment and how we have a phase transition from austenitic to martensitic phase in the places of very high mechanical load. Next, please. This was confirmed also with the diffraction experiment. You see here on the left, we see the diagrams where the points are the imaging, no, the points are the diffraction experiment, and the line is coming from the tomography experiment. So this means that we have almost quantitative investigation of the austenitic and martensitic phase in the material. Next, please. If we increase the coherence of the beam, then we can perform grating interferometry experiments where we are sensitive to refraction in the material or phase propagation. So next, please. For this, we can use line grating. And with monochromatic beam, this means that we increase the spatial coherence of the beam. And with this coherent beam, we can actually produce some interferential pattern using a phase grating, which is the yellow in the middle. And this interferential pattern can be analyzed with analyzer grating. Next, please. This can be used for investigation of magnetic materials and give us some information about the domain walls of magnetic materials. Next, please. Next. So you can see that domain walls are scattering the neutrons, and in this case, the amplitude of the interferential pattern is disturbed. So in this case, we see the domain walls of magnetic materials. Next, please. And you can see, next, on the example here, that on the very right side is the absorption contrast from a very thin iron silicon single crystal, where we don't see anything. And applying the grating interferometry due to the changed amplitude of the interferential pattern, we see the domains, the magnetic domains, walls of this plate. Next, please. This helps to perform a tomography experiment and to see the domain structure of this iron silicon bulk sample, and to confirm that the crystal thickness depends on the thickness of the crystal, and also to prove a certain theory using this type of investigation. So next, please. The neutrons have a magnetic moment, and if we use polarized neutrons, we are sensitive to magnetic fields and can convert this in contrast. Next, please. The magnetic moment of the neutrons is precessing in external magnetic field, as shown here. We can use a polarizer to polarize the neutrons or select only one certain orientation of the magnetic moment of the neutrons. And if it passes through a magnet, then the magnetic moment of the neutrons is precessing, and we can use analyzer in order to convert the precession angle to contrast or to intensity. So on the bottom is shown how the rotation or the precession angle is converted to intensity. So next one. We can use this polarimetric setup in order to perform experiments with different orientations of the magnetic moment of the neutron and analyze after that, after the precession angle in X, Y, Z. And this gives us chance to reconstruct the vector field of the magnetic field. So next one. So this is a small solenoid. And if we apply a current, then we produce a magnetic field. And you see here for orientation of the X or in the X direction of the spin, we can analyze the precession angle in X, Y, Z and perform tomography. So from these 9 tomographies, it is possible to reconstruct the vector field. So next one, and quantitatively. So on the top is the calculation, in the middle is the simulation, and on the bottom is the measurement of the magnetic field which is produced from the solenoid. Next one. We can use this type of tensor tomography in order to reconstruct a complex magnetic field. This is magnetic field which is trapped in superconductor. So this is type 2 lead material. So this is type 2 superconductor where the magnetic field can be trapped in there, and we can perform a 3D visualization of the vector field in the sample and around it, of course. Next one. So here I want to stop with my talk, not to borrowing you so much. So as a conclusion, the methods which we developed at the neutron imaging instrument Conrad 2 have served to a broad user community. We improved the spatial and temporal resolution, which give us unique conditions for experiments in different scientific fields. Unfortunately, this instrument stopped its operation due to the shutdown of the research reactor BR2 in 2019, but the scientific know-how and advanced hardware will be transferred to the research reactor ILL in Grenoble in the frame of one joint research unit. So here, next one, please. I want to thank you for your attention and wish you a very nice day. Thank you.
Okay, so thank you, Prof. Nicole, for very interesting presentation just now. Okay, I hope that we get lots of knowledge from the uh, presentation from Prof. Nicole. So without further ado, we will continue with our last presenter, which is Encik Muhammad Rafi Muhammad Saleh from UNICEF with the presentation titled Relationship between radioactivity level associated with health risk in Borneo. So, Mr. Rafi, the floor is yours now.
Okay, thank you, Chairman. Assalamualaikum warahmatullahi wabarakatuh and good evening. Okay, first of all, I want to thank the organizer for their effort to give me a chance to present, to give my presentation. Actually, I just want to introduce my research. Okay, the title of my research is the relationship between radioactivity level associated with health risk in Borneo, which is Sabah and Sarawak. Okay, next. This is my team members. Mr. Harunizam bin Idris from Malaysian Nuclear Agency, Mr. Muhammad Zaini Yaakob from UNICEF, Dr. Wan Muhammad Zaridan Wan Hassan from UTM, Mr. Faisal bin Yahya from UNICEF, Dr. Boon Siong Wee from UNIMAS, and Dr. Muhammad Rupani Sulung from UNICEF. Okay, next. As we know that over 80% of our exposure to radiation is from natural sources. Okay? There are no detailed terrestrial radiation radioactivity studies that have been carried out in Sarawak and Sabah. Okay? Just do it in Peninsula. However, it is necessary to assess the natural background of radioactivity to provide radiological baseline data. Okay, because we want to know that the population have risk. Yeah, the natural radioactivity can be found almost everywhere in soil, water, air, and the universe. Since it poses a measurable exposure to human beings, the study aims to provide baseline data of terrestrial gamma radiation dose rates, TGRD, and natural radioactivity concentrations, and their correlation with radiological health hazards to the populations. TGRD will be measured in situ technique by using an environmental survey meter. While source samples will be collected and then analyzed using gamma spectrometry system to determine the natural radioactivity concentrations. The results that was obtained will be used in the computation of population radiological health hazards, such as external or internal hazard index and lifetime cancer risk. Using geographical information system software, all the assessment data obtained will be plotted and digitized as an input to establish the exodus contour and exodus concentration distribution to the map of Sarawak and Sabah. Okay, the model will be developed to calculate their correlation with population health, and the output from this project very relevant to the Malaysian national policy on the environment, particularly in realizing its main objective, which is to achieve a clean environment, safe, healthy, and productive environment for present and future generations. Okay, next, please. Radiological mapping has been done in Peninsular Malaysia, but no detailed natural environment radiological studies have been carried out in Sarawak and Sabah. Population health risk due to exposure to the natural radiation source are unknown. Okay, no base reference level for future change in the radiological environment due to human activities or transboundary nuclear event incidents and their relation to population health. There is a significant correlation between the in situ measured terrestrial gamma radiation dose rate with underlying geological formation and soil type of the study area, and also the health risk to the population. So a research is needed to establish measured background data of natural environmental radioactivity and terrestrial gamma radiation dose rate. Okay, a study of relation between the terrestrial gamma radiation dose rate measured with the existing geological formation and soil type can be used to assess the public radiological health risk due to exposure to natural radioactivity based on the radiological mapping. Okay, next please. Okay, our research will be conducted in six major steps or procedure. The first stage is literature review and planning for the research. Stage 2 is fieldwork measurement and sampling. Okay, we will plan and then the location points for field survey measurement and sampling will be identified. Okay, then preparation of research expedition, research material, fieldwork tools, and associated equipment will be done. Then there are in situ measurement of natural radiation in the study area and field. And then soil sampling. And so sampling in this study area will be performed. Okay, stage we will do the data analysis and processing. Okay, the acquired TGRD measurement data will be compiled. Concentration of natural radioactivity in the collected sample will be analyzed. Then statistical validation, correlation, and normality tests on TGRD and natural radioactivity data result will be performed. Correlation of the obtained data results with underlying geological formation and soil type of the study area will be identified. And then stage 4, we will develop radiological digital map. TGRD measurement and natural radioactivity analysis data result will be digitized into spatial format. Spatial and geostatistics analysis will be run, hazardous contour and ISO concentration distribution map for the whole study area will be developed. Baseline natural radiological in form of digital version map will be integrated and generated. And the last stage, we will do the radiological health risk and impact assessment. Yeah, public population radiological health risk due to exposure to natural radioactivity will be analyzed. Population radiological health impact due to the exposure will be evaluated. Preventive and protective safety measures to avoid any significant danger to the population will be identified. Okay, next please. What we expected from this research is it is that the result from the research will be the establishment of background natural radioactivity with the form of radiological digital map of Sarawak and Sabah. The other one is the results of the population radiological health hazards impact values based on the natural radioactivity. The last result is the identification of any significant risk to the public due to exposure to natural radioactivity. Okay, lastly, I want to thanks to Malaysian government for providing the FRGS grant to our team. And our gratitude goes also to University Selangor and Nuclear Malaysia for supporting my research. Okay, that's all from me. Thank you very much.
Okay, so thank you, Mr. Rafi, for very interesting presentations. Okay, so with this, we have reached at the end of our conference for today. So on behalf of the organizing committee, I would like to say thank you for those who joining us, okay, for this session, either through WebEx or YouTube. Okay, your supports on this conference are very appreciated. And also, I hope that we can see you guys again tomorrow, okay, for the for our second days. Okay, so thank you very much. Okay, see you tomorrow.